Okay, so welcome to Talks track number 2. I hope you had fun at the keynote. Now for the talks, just a few more organizational points before we get started. I think some of them Mike already told you in the introduction, but redundancy is not bad. So maybe there's some redundancy. So you might have noticed already during the keynote, if you were in the keynote room. Okay, there's a phone in my background now. Do you hear the phone? I guess so. I'm just going to continue. So you might have noticed that sometimes there's an echo that you hear, and that's probably because people in your vicinity don't mute their microphones, and there's sound leaking from their speakers, loudspeakers, into their microphone. So when you stand next to them, you hear an echo. So please, if you're in a room listening to a talk, please mute your microphone whenever you don't want to explicitly talk to your neighbors. So if you hear the echo, then you can I think you can mute others. So you might want to try that if that works by clicking on the mute or the microphone symbol. And if that doesn't have, or if it doesn't work, you can try quiet mode. I think on the Mac it's Command U, and on Windows and Linux it might be Control U, or you can just click on your name on the bottom, and then there's a turn on or turn off quiet mode menu item there. Speaking of this menu that you can open when you click on your name, you can enter a small description or a small bio of you. For example, you can put in your pronouns, your preferred pronouns, if you like to do that, or some preferred languages or languages that you speak. You can put them in this little box underneath your name. That makes it a lot easier for others to talk to you during the conference. So, and what else do I want to tell you? During the talks. So I'm the moderator, and you can post any questions for the Q&A to me directly in Gather. So I'm the one standing up on the stage right now. I'm a staff member, so everyone whose name includes staff, you can you can ask things about the conference in general, but whenever someone's on a stage, he or she is probably a moderator, so you can ask the questions for the Q&A to him or her. Yeah, so speaking about questions, what else do I want to tell you? I think there's nothing more. Oh, yeah, private chat would be preferred for the questions. That makes it easier to not have any spoilers. And I, as a moderator, try to, as Mike already said, try to spin a conversation afterwards. So please prefer to ask questions via private chat. The chat is not easy to use. It's a bit confusing at times. So down at the bottom, you can post messages nearby to everyone or to a specific person. But I think you can see all the messages that your private messages or nearby or everyone in the chat above. So please don't be confused that whenever you think, well, I'm talking to this one person, you might see other person's chat messages appear as well. Okay, now that's that stuff out of the way. Let's begin with the talks. I think when you had a look at the program yesterday, you might have been very happy and thought, I want to see, or up to yesterday, I want to see Andres Lö talk about effect systems, I guess. But sadly, we had to change that. So there's a replacement. We had to make a replacement there. So the talk is now by some guy. What is it? Let me open the program really quick. He's called Markus Schlegel, I guess. I hope I pronounced that correctly. And he's talking about composable UI components. Markus is a what does it say? Software architect, whatever, okay. He tries to liberate programming from the von Neumann bottleneck since 1991. What's that? Well, he's also interested in a diverse set of technologies ranging from UI design to concurrency to and so on and so on. And then what is this? In his spare time, Marcus reads a lot of Marx. Okay. Well, anyway, so there's Marcus Klegel with Composable UI Components coming up right now. Oh je. Soll ich Sakko noch anziehen? Oder bist du übertrieben, oder? Meinst du? Okay, so hello everyone to this talk on composable components. That's composable UI components. So we're talking about user interfaces in the modern style, such as with things like React or Angular or these sorts. My name is, as this other guy just said, Marcus Schlegel, and I'm a software architect at Active Group. Now, as for my motivation, what do I want to talk about? Well, composition. Well, don't we all want to talk about composition? And of course I want to talk about reuse. And well, to be absolutely precise, I don't want to talk about composition and reuse. I want to talk about composability and reusability. There's a slight difference. I hope that will be clear during the talk. Will become clear, that is. Now, there's a lot of talk about composability and reusability and composition and reuse, but I think there's an underlying concept that's not talked about that much, which is that, well, code changes, and so there's movement of code, and just like saying it like that, it sounds obvious. Like we all know that code is not like there's no static project that's ever done, right? But I don't think we always get all the consequences of what that means, right? Of the movement of code. And so I want to be a bit more explicit on that during my talk. Now, to drop a small Karl Marx quote on you, this is a quote from the first volume of Capital, where Karl Marx talks about his scientific method, and he's analyzing, well, as you all know, Karl Marx analyzed capitalism with a special method which he called dialectical materialism, and he characterizes dialectics as something like this quote. He says that we have to regard every developed form as in fluid movement, and therefore take into account its transient nature not less than its momentary existence. And of course this all sounds like totally obvious, but well, as Karl Marx showed in Capital Volume 1, the consequences are not that obvious, and they are quite consequential indeed. And so I want to take that very same method and apply it to code and programming. You might think, well, could there be any two things further apart than programming and social relations like in capitalism? And I think, yes, it is quite close actually, because programming, after all, is also a social activity. But to move a bit further to the ground and get a firmer grasp on reality, let's first talk about what I mean with the term composability, for the sake of this talk at least. So as we all know, we're functional programmers, right, at Active Group especially, and I think Bob Konf shows that we like to talk about functional programming with others as well. So of course I have to start with a function, and this is a simple pure function. This is JavaScript, but it doesn't really matter what language this is, or what the arguments work in any language. So in JavaScript you define a function like that, and it's got a name, right? It's inc, and it takes a value x and it returns x plus 1. So it increments integers. So it's as basic as it can get. But there's not something underneath here, right? So we don't just do functions, right? There's usually a problem that we want to solve. And the problem behind this solution, which you can see here, is that we want to increment integers. But problems, they have the tendency, at least in our business, to change. And of course, for the sake of this talk, the problem changes also. We don't want to increment integers anymore. We want to do something similar, but not quite the same. We want to take tuples of integers, so 2 integers now, and we want to increment them like each part. And as you can see, I added something to the slide in the middle, and that's a new snapshot of our code base. And as I said, I want to draw attention to the movement of code, and that's why I display them side by side, these 2 snapshots. Like the first one that we saw in the beginning, it solved a very specific problem, and in the middle we had to change something. We had to add something, to be precise, to fit the new problem description, right? The solution has to follow the problem, which is quite obvious. But we can see it does follow the problem in quite a specific way, because we didn't have to change anything per se. We just added something. We just added another function. Excuse me, another function. Of course, it needs a new name, inc tuple, and we reused the old function as is, so we didn't have to change the old function. And that makes sense, because the 2 problems that we had, incrementing an integer and incrementing a tuple, they have a combined, like, unified kernel inside, which is like incrementing stuff. And so we would like to follow that property in our solution as well. Like, we want to have a common kernel that's not supposed to change much, right? And that's why we can reuse functions. That's what we want to do, right? We want to analyze the movement of code and simplify things in the movement. And of course, we're not done now. Always be composing, so the problem again could change slightly, could get bigger still. And well, it's quite a contrived example now, but you get the idea. We still only have to add something, another function, if the problem allows for such a style. Yes. And that's basically all that's inside of the, like, that's basically all that the term composition of functions says, right? You want to combine small functions to build large functions. That's a common theme in functional programming. But functions are, well, they're not boring per se, but they're quite well understood, I would say. But we want to have the same benefits that we get with function composition with the composition of other things. And one of the things I want to draw focus on in this talk is UI components, of course. We want to have composable components, yes. And so the composition of UI components is simply that: combine small components to build large components. And again, it's important that we not just want to combine them in any way, but we want to combine them without changing the smaller parts, right? Ideally, if the problem allows. And we can have a look at the current state of the art with React in this case. This is a React, they call it function components, function component, and we're using these hooks, right? You see this use state, that's called a hook, and that's what makes it not really a function anymore. It looks like a function from the outside, function counter, right? But there's stuff going on inside which makes them only sort of pure in a very broad sense, so not in a pure functional sense. And now what this counter does is, well, it counts, right? It displays a button with a label that's a number, and when I click the button, then it increments the number, and I can do it again and again. So simple problem again. I think it's maybe one of the most simplest components you can come up with. And the implementation that you see here is reasonable, right? It works, so it fulfills the specification of the problem, and it's reasonably short. So, well, arguably you couldn't do much better. So just to go into the details a bit, for those who don't know React that well, so as I said, this use state is a special construct. It basically says that you have a state, and you can get two things out of this call of use state, which is the current state. So React has this idea of a rendering, and the state here refers to the current value of the state in the current rendering. And then you have set state, which is basically the writing part of the state, so an update. And then you say return. That's a bit strange syntax in my opinion, but anyway, you display a button like this. This should look like HTML, and you have an on-click handler, and it in the on-click handler you call the set state, so the write with the state +1. So when you increment a value, and then of course the button needs to display something. So that's this state right here. That's just the current counter value. Now, as I said, this is fine. It's not like it fulfills all the needs. But when a problem changes, we get into, well, problems. Because now the diff, like you see again the before and after, and I made these little annotations with pluses and hash signs. Before, with functions, we only had pluses, so we only had to add something, and what we already written down, we could just leave it like that was fine, right? But now that's not anymore. That's not the case anymore, because in order to solve a larger problem, we almost always have to adapt a solution for the smaller problems. In this case, we now want to display two counters, so a counter for a tuple of two integers, and of course we have to add a new component. That's the part down here now. Do you see my mouse? Yes. Okay. So that's fine. There's something has to be done, right? Can't really change much about this. But this part up here, as you can see, a lot has changed. What we did was we made, oh, okay, there's a step in between. I'll come back to that. What we did was we made this counter a controlled component. That's a term in React. And the control component is basically characterized by, well, it doesn't manage its own state. It has a value and on change prop, so argument passed to it, and it has to display the current value in some fashion, and it has to call this on change whenever it wants to update its controlled state. Okay, let's go back to these things. Okay, so the problem statement also includes, for again, to make my argument a bit more airtight, is that we want to also display the sum of our tuple values, right? That's going to be here. And that's the reason why we need the use state thingy in this larger component, right? If it were down in the small counter component, we couldn't access it. We couldn't compute a sum. So that's why we need the values up here. That's why we need to change things. The use state is now in the toCounters component. And again, we get a state and a set state, and we call them accordingly. As I said, the counter has to become a control component, right? There's no way around it. And well, we use a control component by, well, passing down these two values, value and onChange. The value for the first counter component is going to be the first part of the tuple, which is referred to by the state identifier here. And the onChange is just basically going to be a shove into the first part of the tuple, and the second part stays the same. So this basically this says it stays the same, right? And we get a new XX, so a new updated first part, and we just put it where it belongs. And the same, but sort of mirrored, is happening in the other counter component. So we can place two counters here, pass them their appropriate values, and we're done, right? But we had to make this up here a control component in order for this to work. But it's getting worse and worse the larger our programs get. So we're not done yet, of course. Always be composing. There's now this contrived two counters, which we want to use the two counters for that. So we have a tuple of tuples, I should say that. Tuple of tuples. But we can't, because it's not a control component. We have to make that a control component in order to use it. And so the diff looks really, really bad. We have to change a lot of stuff. And now my face is in a way, but I highlighted these lines again. You can see that what we do whenever we use a control component is a bit well, cumbersome. There's a lot of, it looks a bit dense, even though what we do is, when I want to describe it in words, like in simple words, it's really easy, right? We want to sort of focus on the first component of a tuple here in this part, and we want to focus on the second part of a tuple down here. And well, focusing means take the value of the first part, and when you have an update, well, you put it in the first place, in the first part, right? And in the second, accordingly. Now, whenever we have a lot of complicated code, and we are able to verbalize what's going on in much simpler terms, in functional programming, that means it's a code smell, because we have all these great tools at our hand to not have to verbalize, like and write it down in a comment, or write it in a README, or tell it like via speech to a coworker. We can just write an abstraction or write something down that captures the essence of what's happening here. And that's what we are now gonna try to do. And in order to be able to do that, we need to talk about lenses. I already alluded to, maybe you noticed, to lenses by saying we need to focus on a specific part of a larger structure. That's basically what lenses do. I tried to visualize what lenses do in this picture right here. So you see an arrow pointing from a larger structure into a substructure of this large structure, and this arrow is what represents a lens, what a lens does. You can think about a lens as an arrow. It's not quite right if you if you think more about it, but for the sake of this talk, you can think about it as a simple arrow into something. And a store you might not be familiar with, especially because I think I made that term up myself. And well, a store, for me or for this talk is a lens plus a large data structure packaged together, right? So so in this case, this orange arrow packaged together with this blue larger pentagon, I think it is, that would mean you have a store. And lenses allow for, well, sort of reading and writing, and they compose, and so our stores follow the composition and semantics of lenses roughly, and so so hopefully they also compose in the end. In order to make them, well, worth anything, we need a few operations on our stores, and the first one is a simple read. And try to visualize it again with these shapes. Read of such a store is just the part that's pointed to in the larger structure, right? So read would give you the smaller square in this case. Excuse me. And as the headline suggests, there's also writing. So we have an overhaul function which takes a store and returns a store, but not like, it's almost the same store. The output is almost the same store as the input, except for the part that's pointed to by the lens. That's replaced by a function that we also put into overhaul. So the function maps the square to a star, and so the output is the larger structure as is, but the arrow now points to a star. So there was a replacement going on. And it's not just reading and writing, it's composable reading and writing, so we need a combinator. And the combinator that we want is basically a lens composition, sequential lens composition. So imagine a lens as an arrow. You can just take two arrows and put them end to end, and they form a larger arrow. That's, well, just the path these two arrows follow. And again, a little visualization. We have an orange arrow pointing at some structure inside a larger structure, and then we have a what is this? Red arrow that's pointing again at an even larger, even smaller structure inside this this square. And so if we say we want to focus this store with this smaller lens, then we get another store that's basically the old one, but with a lens composition going on inside of it. And now we want to try out our new notion of lenses and stores. We write a little, very, very tiny library with this idea. And I can show you, but it's really bad and only like 20 lines. Instead, we want to just look at an example. Like, how would we use such an API that's based on the idea of stores and lenses? And again, we have this problem of the counter. We want to have a button that's that displays a value, and whenever we click it, it's going to be incremented. And with a new idea of the stores and lenses, the implementation would look like something like this. Now, first of all, we have to have a convention, or what is it called? Like we have to agree on something in that we now need to have stores passed as an argument to every component that we want to write, right? And that's going to be, well, this store keyword right here. And this store now represents a value that the component is about, right? So you can think of a UI component as managing some data, and the data is, in this case, represented by the store. A UI lets the user read or, well, look at the data, and it also lets the user manipulate the data, and that's what we do here with the overhaul and read, right? So instead of as before, we were calling set state and calling set state, for example. We now use our overhaul with a store that we're given and a function that increments an integer, right? In this on-click handler right here. Oh, my mouse. In this on-click handler. And displaying the value, well, we already learned that you can get to the current value of a store by calling read. Now, as we saw, read store, overhaul, store, and a function. And now we want to change the problem again, right? We had a single counter, single integer that's going to be incremented. And now we want to move to a larger problem, that is two counters for a tuple of 2 values. And now, of course, the diff looks much better because this counter that we wrote in the first installment was already composable, right? Because we followed this one convention, is that a right word? of passing a store object. And well, we couldn't do anything else than overhauling or reading with it. So we did that, and that already makes it composable. And we see why that is when we look at our combinator, of course, the focus function. In that, for the 2 counters component, we of course also get a store, right? That's our rule. Now this store, it represents the value of the 2 counters component. So it doesn't represent a single integer, it represents a tuple of 2 integers. And so we can't just pass this store down to the 2 counters that counter button components that we want to display. That would be wrong, right? They would like read something and display a strange tuple. That would maybe work, but this update of x plus 1 doesn't make any sense for tuples, right? So we have to manipulate the store that we're given in some way. And the only way we can transform stores is our combinator. And so we call our combinator, and well, what do we want to do? We want to focus on a specific part. And this right here must be a lens. So I invented some lens library here. And the lens library, it comes with a set of standard lenses. And this standard lens right here, it's a lens into an array structure. So into the 0th component of an array in this case. So we just focus on this part and pass down the store that's falling out of this function invocation. And then in the other installment, we just use a different lens, right? We want to focus on the second part of the tuple. So we use a different lens, slightly different lens, and pass the result down to the other counter. And this works, right, if you have the proper library behind there. And we're also not done, of course. Always be composing. There's an even larger problem probably waiting around the corner. And if the problems do have a common kernel, then in this style, you hopefully don't have to change much again. So, in summary, composable components, what did we do here in this talk? Well, we kept an eye on the movement of code. That was sort of our method. I didn't go into the details during the later part of the talk much, but we always saw that we had these like different snapshots of the same code base, we could say. And the interesting parts happen in the diffs, the diffs between 2 snapshots. And I think we can only really understand what software engineering is if we think about the movement of code and not just of static, like give me a to-do MVC implementation and I can only tell you like some minor details about it, but you should give me the progression of a to-do application in order for me to judge, to be able to judge if the underlying programming model is is compositional or not, or is adequate or not. Then composability allows for lossless reusability. That's sort of a what our method told us by looking at a certain instance of a part of programming, which is UI component front-end programming, a large part these days. And in this specific case of UI components with React, we notice that controlled components are composable. That's quite nice, and they're therefore reusable, but they're sort of cumbersome and they don't really express the essence of what's going on. You have to always pass down these value and on-change thingies. They obviously have to fit together, right? You can't just do completely random stuff there, but this controlled component style doesn't allow you to express the essence of what's going on. And that's what lenses, and in this case stores, are for. They allow for lossless composability as these control components do, but they don't have this contrived, cumbersome whale around them. And that's basically all I wanted to tell you, except here's a little to-do list for you. This talk is sort of based on a very old idea by Cornell Elliott. I think this talk that I link to right here is from 2006 or something. And Cornell Elliott, he argues that components, or in his case UIs, graphical user interfaces, are tangible values. He wants to he's interested in what these things are, right? And he argues that they're tangible values, and there's a lot of interesting properties falling out of this insight. And if you're interested in JavaScript lenses in JavaScript, this is the lens library that I used for this very, very small example. I cannot really say anything good or bad about it. It's just the first that I found that has an identity lens. So, right. And of course, the most important one is this thing right here. That's a ClojureScript library, React C. That's sort of this idea of composable components taken to the 3,000 steps more than what I just showed you. There's a lot more going on there, but the basic idea is the same. So you have these tangible values, you have these composable components, and a lot of reusability falls out of that. Thank you. Okay. Welcome back to the Q&A. So if you have any questions, please post them via private message to me, who is Markus Schlegel, up on the stage. So far, I think... there's a question already. See, I couldn't really... okay, there's a stream delay probably. So now there's a question. Let me read it real quickly. I'm just going to read it. Joachim asks if if a component gets a store in a lens, but it seems it can't do anything with the store beside the operations enabled by the lens. Yes, that's correct, basically. And the lens can only be used with that store. Why pass two things and not a store plus lens object? I'm not sure if I understand correctly, but it's the store idea of a store is that it packs some data and the lens, right? So that's why you only have to pass the store. And then you can manipulate the store via a lens. So on the boundary between like a component and a user of that component, there you need another lens to manipulate the store that you're given as a user, right? But that store already includes a lens, sort of like underneath, not really accessible directly, but you can manipulate it via a new lens, and you get a new store out of it. So you don't have to pass two things. You have to only pass the store, and the store includes both of these things, both things. Like you could even say that's an implementation detail, really. Like a store is a store, and you can get stuff out of it, and you can overhaul, like you can manipulate its data, and you can combine it with a lens, right? That's the three things you can do. Okay, another very interesting question, of course, that I skipped over during the talk is, where did the initial store come from? I said that every component needs to be given a store, yes, but you have to start somewhere, at one point in time. And well, yeah, that's just, you have to, like, when you start up the system, there's a special like runner or something like that, where you can create a new store, or you can initialize a new store with basically an identity lens into some whatever you want to give the topmost component. Like in the example with the tuples, you would just write down an actual tuple with some actual values, like 0, 0 or something like that. So that would be the initial render, would get this initial store. And then from then on, it's compositional, just like maybe the components themselves are compositional, but not the program that has to initialize, necessarily has to initialize at some point. That's just your application then. Okay. Okay, Joachim clarifies that. Yeah, I think my answer to his question was satisfactory. What kind of challenges can come up when using lenses, and in what situations do these arise? Well, we're talking like the examples in my talk with JavaScript. I don't really actually know JavaScript, to be honest. I've never written it more than for the sake of this talk. I usually write ClojureScript, right, which is a bit different, but it is the same in the as regards to static type systems. So there's no static type system of like no mentionable static types, at least, with both JavaScript and ClojureScript. And so you can run into like all sorts of problems there. For example, you are sometimes inclined to provide lenses, in quotes, that do some stuff that don't follow the lens law. So they're not actually lenses, but the language allows you to write. I think you would even, like, even a static type system, you could write lenses that don't satisfy the lens laws. But it's even easier in ClojureScript, for example. And so you have this idea in your mind how something complicated has to work, and you know that a lens has this basically two parts, right? And then you write these two parts just so they fit your whatever you have in your head, and they don't actually follow the lens laws, but you think, it might be fine in this instance, and that's almost always a recipe for disaster, of course, because it might be fine in the specific instance that you think about, but it really is it makes sense for these things to be lenses, and to follow the lens laws, of course, because there are always cases where the system, like the underlying system that manages this, like the framework, basically relies on certain properties, and if you don't follow the lens laws, then these properties don't hold, and things go bad, of course. Okay, so there's no more questions, and that's very good because we're also running out of time. Thank you very much for listening to my talk and listening to my moderation on my own talk. I hope you noticed that it was the same person, actually. And there's a longer break now, I think about 35 minutes or something. So you can grab something to eat or get a coffee or talk to anyone who's at the conference, who you'd like to talk to. Have fun. And we're back again with the talks. You're currently in room number 2, or at least you're watching stream number 2, or the track number 2, that is. And so there's 2 talks that are coming up. The first one is Compiling Anything to Categories by Greg Pfeil, who is with me now, but you can't see him yet. Only after the talk we'll have a quick chat with in the Q&A. So if during the talk any questions come up that you want to ask Greg, then please write a quick private message to me. That's Markus Schlegel at the front. I'm on the stage. You can just write a message to me at any time during the talk. You don't have to wait until the Q&A, especially because we have this a bit of stream delay. So if you write your question early, then we can start early or start on time with the Q&A. Again, a quick reminder, if you hear any echoes, that might be because people in your surroundings didn't mute their microphone. You can just go into quiet mode. That's Command U or Control U, or you can find the menu on the lower part of the screen to enable that. But that's enough talking of me or by me. Let's cut to Greg's talk about compiling anything to categories, a talk based on a now famous, I think, paper by Conway Elliott. Greg is working at Kitty Hawk, where he helps them get Haskell off the ground, even though he doesn't really know only very little about planes. He writes of himself. When he's not working, you can usually find him holding his breath underwater just off the coast of Maui. So I'm very excited for this talk, and please give a virtual applause for Greg.
Hi, I'm Greg Pfeil, and today I'm going to talk a bit about compiling the categories. If you're not familiar with the project, it was a paper about 5 years ago from Conway Elliott. I'm not going to go into details of it, but it's fundamental to all the work in this talk, so it's important to have at least some idea. The paper relied on earlier work that showed that the models of the lambda calculus are exactly the Cartesian closed categories. And also there's a transformation from simply typed lambda calculus to the vocabulary of CCCs, Cartesian closed categories. This means that any lambda expression has an interpretation in every Cartesian closed category. Conal realized that Haskell is pretty much lambda calculus, right? And so we should be able to translate arbitrary Haskell code to a Cartesian closed category of our choice. So he implemented this as a GHC plugin that would basically take GHC's core representation, which is the most lambda calculus-y of Haskell's intermediate representations, and rewrite it into the vocabulary of Cartesian closed categories, interpreting into whatever category you want. So what does this mean practically? Well, all sorts of things form Cartesian closed categories. Other programming languages, computer hardware, reverse mode, automatic differentiation, etc. So instead of working within an EDSL or some other external approach to kind of work in the domain, in these different domains when you're working in a Haskell project, you can tell GHC via type class instances how your target category, or how your target domain forms a Cartesian closed category, then indicate in your code which bits of Haskell you want to interpret in that category. One neat thing about this is that it doesn't work at the level of programs, right? It doesn't take like a whole Haskell application and then treat it differently and spit out, a different application that works in that domain. It integrates much better than that. It works at the level of functions, and so you can basically write your functions in Haskell and say that you want individual pieces of that to be interpreted in a different context, and then still use the results of that different interpretation in the larger Haskell context. So here's the overview of what I'm going to talk about now that I've given that introduction. What we're using this for, what didn't work for us, what we improved, how to use this plugin, and what's left to do in the plugin. So we are Kitty Hawk, which is a company building the next generation of flight. Unlike most of my other talks where I have to disclaim this, here I can say it. Yes, we do use what I'm about to talk about at work in a very fundamental way. So we use it for getting this plane into the air and keeping it up there. So I'll do brief pitch for the plane. So the vehicle is called H2. It's a single passenger, remotely piloted eVTOL, which is an electric vertical takeoff and landing vehicle. It's a real thing. It actually flies. The propellers tilt to convert from helicopter-like lift to plane-like forward propulsion. There's multiple test flights, multiple days a week in both remote pilot and autonomous modes. It can land in an area way smaller than a helicopter. It's much lighter and quieter than a helicopter and can travel at 156 knots. Really, it's pretty neat. So we have a bunch of these vehicles and more are being built regularly. It's still in development, so for the most part, each one is a little bit different from the last. Also, the flight control system for this vehicle is written almost entirely in Haskell. Actually, that's pretty cool in itself, so I guess I can just stop the talk here. TLDR, we have a plane flying on Haskell. That's not really a common thing in the aero industry, but it was already in place before I even started at Kitty Hawk, thanks to Greg Horn and his team of adventurous controls engineers who really took on this project to do something very different from every other project in the industry. So what did we do to take this already cool project and make it even cooler? Well, when I was hired, here's where things stood. We had about 30,000 lines of Haskell code in hundreds of modules to define the flight controller. It was actually quite cool. We used a higher kind of data approach to allow either direct interpretation of the Haskell or interpret the Haskell into an AST that would be used to generate the C code that's compiled to then run on the aircraft. And you've already used the word interpretation twice on this slide, so you might see where this is going. The higher kind of data approach, though, had a few complications. One, it required redefining the most basic stuff so that we could define instances over various higher kind of data functors. For example, we had to redefine if then else, all the Boolean operations, ordinal operations, and everything from there on up, right? So it required extra type parameters, which had very rich sets of constraints that basically had to be passed around through practically every function in the whole system. Since any code that could become part of the controller needed to be aware of higher kind of data, it meant that we couldn't use third-party libraries for anything core to the system. So we brought in Konf's concat, that's the name of his plugin, to move a lot of that complexity into the compiler and allow the controls engineers to write the same kind of Haskell everybody else does. That meant we had to define our own Cartesian closed category, one for our CAST. For this, we took advantage of large parts of what already existed from the higher kind of data system. It's not the meat of this talk, but it's been open sourced, and we hope it's a generally useful application of the compiling the categories approach. As I already mentioned, you can interpret the same code in multiple ways. In this case, we can both use the Haskell code directly, creating a program that, well, is a flight controller in Haskell. This is useful during development for things like GHCI, where we could debug the library, of course. We could alternatively run the code through the plugin and get out the result in our target category, again, the AST for C. And so when we run the Haskell program that's produced by that, when we run that Haskell program, it outputs a bunch of C code that we can then compile to the plane's architecture and get onto the plane. So we generate a subset of C, which is with guaranteed inbound array access. There's no nans, has deterministic runtime. And we have a randomized expression generation system that ensures that the original Haskell and the generated C paths both produce bit-for-bit identical results, which is what allows our controls engineers to confidently use GHCI during development and not have to always, go through the C path in order to test that their changes are doing what they think they are, or that things are behaving the right way. They can trust that the Haskell is actually doing the same thing as the C would. So, we really hope that this category that we've defined here is useful. I caution against looking at it as an example of the approach at the moment. It still has a lot of baggage left over from the higher kind of data stuff that we pulled into it. And of course, it contains some stuff that drifted as we settled into the compiling the categories approach ourselves. And so we're going to keep working on it, of course, and hopefully some of that baggage will go away and it will become a better example. But even if it's not a great example, it is hopefully a very useful category, that you may use in your own projects if you need to produce C code. But Konal's work, his concat plugin didn't actually quite get us there. He provided a huge foundation, but his plugin kind of required your code to be written with the plugin in mind. What I mean is basically the plugin can handle lots of stuff, but if you just wrote normal Haskell code, you were bound to bump into edges that weren't supported. And so you would have to translate that to things that were supported and rate things in a special way that didn't mean anything different, but we just couldn't handle all Haskell code. One thing was the case is that inlining had to be handled very carefully. So it made it really difficult to use functions defined in other modules, and especially like third-party libraries that exist. And so, we had 30,000 lines of existing Haskell code that flew on our plane, and we weren't in a position to rewrite all of it to meet the limitations or restrictions of Kernel's concat plugin. For example, it didn't support sum types. There was no support for recursion in it. It was quite slow due to some design choices and definitely a number of other things. And again, like when Kernel wrote all this, it's very much a proof of concept. He's showing that like this is even possible to do, and that alone was so important for our work. So we really built on top of all of his effort that got to that point. So we wanted to be able to compile anything to categories. Rather than rewrite the code that Kitty Hawk already trusted, we wanted to extend compiling the categories to work for all of the Haskell code we already used, and to get it polished enough that others could easily do the same and use it for their own purposes. Really, since I've started working on this project, I've had people coming up to me and ask when they'll, actually be able to use compiling the categories because they've tried kernels and ran into some issue or other that made it too difficult for them to work with. And thankfully, through Kitty Hawk, we've had the opportunity to really dedicate the time to overcome a lot of those things, and we want to make sure that that's made available to everybody, basically. So as I mentioned, I'm Greg File. I'm a programmer at Kitty Hawk. I work on the tools team, which basically supports other teams there through software, including the flight controls team with this work that I'm talking about today, and also supports flight test with our ground control system and other systems like that. It's a really broad team. It includes things like GTK apps and like log querying systems, flight simulation. But this talk is really about GHC related work for this plugin approach. So I'm giving this talk from Maui, where I live. I try to spend as much time underwater as I can, and I mean that literally. The longest I spent underwater so far is just like over 4 minutes on one breath. I can also dive to like 41 meters deep without any oxygen, just holding my breath. So if you want to get a question about programming or something answered quickly by me, the way to catch my eye is to also ask me something about free diving and my interest in that sport or whatever, and it'll definitely make make me notice your message if it's something you want to talk about as well. So yeah, let me know. Anyway, I am just one member of this team of people that have all worked on this project at various points. All of them have been invaluable in making it happen. I can't imagine any of these people not having been involved. And of course, way more than these people. These are the people who've worked on the code, but the other teams at Kitty Hawk, especially ones like the flight test and controls team, their support has been super important. If they weren't behind this project and believed that we could deliver something with it, we really would not have had the opportunity to spend to make this happen. So I just want to, spread that recognition around. So just about a month ago, we finally managed to get this open sourced. I started working on it about 2.5 years ago. It's no longer what I spend most of my time on, but definitely for like a year and a half, it probably was. But now it's finally open sourced. Kitty Hawk has always been on board with getting it to be open sourced. But it took a while for us to extricate it from our internal code base, especially while it was in heavy development. It became much easier once it was a bit more stable and not constantly being worked on. And we had some legal things to get signed and done before we could actually make it public. But now it's out there. It's on GitHub. You can check it out. You can look at it. It is not yet published to Hackage. I expect that to happen in the next few days, at least for parts of it. Parts of it have other reasons for not yet being on Hackage, like dependencies. But we'll work on getting everything there. We want this to be as easy to use as possible. So let's talk about what is in this project. So we started off forking Conal's original concat plugin. But as we started to work on it, we realized that some of the things that we wanted to do for various aspects of our flight control system were going to be much more involved. So we ended up rewriting the whole plugin, which is very educational. But ideally, in the coming months, we'll work with Conal and others to kind of reunify the plugins to some extent. There's already some pieces that we share between the two, and there are some parts that were forked instead of rewritten, and hopefully we can reconcile the changes that have happened on both sides of those relatively easily and get back to a single place there, and then continue to work through and try to see how we can unify these so there's not kind of a schism in the compiling the categories world. So some of the things that we added support for, like I mentioned before, there was missing some types in recursion. We've added support for those things in our plugin. Having code spread across multiple modules and third-party dependencies. So we use lens and Barbies and transformers and other things like that. That again, we needed to use from the pre-existing code, and so we made sure that we could support that kind of modularity in there. We support alternate type class hierarchies. Conal's plugin is tied very much to his concat classes type class hierarchy, whereas we do support that one. In fact, that is the type class hierarchy that we do use ourselves. But we also support base, with its arrow type class, and Komet's categories type class hierarchy. And so we made that kind of pluggable. We support FFI integration. This is important for us. As I mentioned before, the flight control system is almost entirely written in Haskell, parts of it written in C, and we generated C code, so it worked together like that. So we needed a way to be able to take Haskell side FFI stuff and basically pass it through to the target category. For our target category, it works very well because, again, it's C, but other categories could interpret the FFI code in different ways or somehow use the C code, but it depends on the category you're going to. We added references, basically abstractions in the target category, where again, for our target category, which is C, C has functions. And so rather than taking our whole Haskell program and turning it into like one categorical expression that does everything, we could keep the modularity to some extent, and Haskell functions map directly to C functions. So you get, C functions defined, you get much more readable code with many smaller functions instead of just one massive expression. We improve performance orders of magnitude. Definitely lots of different places to make things happen. But one of the big things is just, again, we're working with 30,000 lines of code, whereas Conal's examples are generally much, much smaller than that. And so any kind of performance issue became very apparent as the code size scaled up. And we definitely run into times when we thought things were non-terminating, but then after various improvements, we could get it to work in a reasonable amount of time. And finally, we added rich error reporting. If you ever used the original plugin, anything that goes wrong basically just reports as oops. And so we kind of took a page from the Rust and DAL worlds to try to come up with very descriptive error messages that also provide suggestions as to how to fix the issue you're running into. And so, of course, we're still a far cry from those particular projects that do such a good job at this, but it's definitely a direction that we're heading in. And any patches that come in that improve an error message or fix typos in them, or suggest a new way around something, are very welcome. We very much support that kind of contribution. So now, how do we actually use this plugin? I've been talking about this plugin, but you haven't seen anything to do with it yet. So this is basically the simplest possible example. Here we define a new category called Hask. Again, this is the simplest example. So Hask is simply a new type around Haskell functions, right? So it does very little. It's practically nothing. And so then we have our category. We have to define the instances that define how it's a category, right? So we have our category instance that says how identity and composition work. which again, they just unwrap that thing through the regular function composition and then rewrap it in Hask. And then there's an arrow instance. As I mentioned before, we can use base, we can use arrow, but arrow, the arr operation, is super powerful. It's very rare that a category can actually implement that. If you can, this is great. This is all you need is a category instance and an arrow instance, basically. You can also add arrow loop if you have to deal with recursion, or you can add arrow choice or other things like that if you need to. But basically, these two will get you pretty far. However, again, it's very unlikely you can actually implement arrow. If you can, this is all you need. So that defines our category for us, everything we need there. Now what we do is we take the standard negate function and we call categorify expression on it, which takes that expression and categorifies it from being in, a function from A to B to being a Hask morphism, a function from A to A in this case, into a Hask morphism from A to A, right? And we give that a new function named wrap negate. That's our categorified version of negate. And again, since this is such a simple case, since it's a simple category, we have wrap negate. All we have to do to get the function back is called run Hask. We can then apply it to the value 5 and print the result. And so running this program will just print -5. Everything is on here except for the imports that wouldn't fit on the slide. So this is using the plugin. But even with this, there were cases. So at Heavysoft, or at Kitty Hawk, we Heavysoft is the name of our software repo there. So at Kitty Hawk, we have separate teams. Right, the controls team is the one that actually writes all of the flight control code in Haskell, and the tools team manages this sort of code generation plugin use part of things. So one thing that happens with this is that the type of wrap negate, for example, is pretty fragile. In the flight control system, they'll make changes, they'll add parameters, or they'll change the types of parameters or things like that. And every time they would do that, it would cause this to break, and they would have to find this code, edit it, and kind of break out of their normal development cycle in order to make small patches to what really they shouldn't have to pay any attention to at all. So one of the first things we did with this was to provide basically a bit of template Haskell to simplify that. So instead of defining that function explicitly with a type and all, we have categorify function, which takes a function name and the category you want to apply it to. That final empty list is actually a list of any specializations you want to apply if there's type parameters that you want to specialize before categorifying it. But this will basically give that same function definition. But of course, if the type of negate were to change, unlikely, but in our project, there are definitely plenty of functions whose types change frequently. This would generate a function that matched that new type and would not require any changes in this area of the code, right? So yeah, that is what I recommend, to use categorify function rather than using expressions and having to kind of deal with that fragility. Yeah. And here is the compile stanza to compile that particular example. There's not too much to it, right? Like the one thing you have to do is provide the plugin, fplugin option, and give it categorifier, which is the module name in which the plugin's defined. And you need to also add categorifier plugin to your dependencies, because that is where that categorifier module lives. And so you provide the module for the plugin, and it will work. So let's look at another simple, again, very simple example. Two things different here. One is that we're using a different category. It's the syntactic category. It's provided actually as part of Conal Elliott's Concat Examples library. It's a great library that has a bunch of predefined categories in it. This is one of them. And the other thing that's different here is that instead of using negate in base, something that we know exists or whatever, we're pulling in, a function from lens. So this is, again, one of the third-party libraries we had to be able to support, and definitely one of the early sticking points with our work on the new plugin. So this basically categorifies the view function from lens into the syntactic category, which basically outputs a textual representation of the categorical expression. So in this case, we categorify lens. We basically call render on it, which again turns the Cartesian closed category syntactic into a string for us, and then we print that string, and we get the comment underneath here is the output there, formatted a little bit more nicely, but this is basically what it looks like. And that is, the interpretation of view in this category. It is, the categorical syntax for it. And this is a little different because, as I mentioned, that syntactic comes from Conal's type class hierarchy, not ours. Not base. And so, so the problem with that is that we need to tell the plugin that we're not using base for our type classes here, right? So it adds one line here to our Cabal stanza, which is we have to provide the plugin with an option. So there's a GHC option called fPluginOp that gives an option to a plugin. And it starts with the name of the plugin followed by a colon, and the rest of that string is passed then onto the plugin. So here, its hierarchy is the next component. So that tells the plugin that this is going to be a value setting the hierarchy to use. And then we provide the fully qualified Haskell identifier for that hierarchy as the argument. And again, we have to add the dependency here, categorifier concat integration. That is the integration that lets us use concat with our plugin, and that provides that type class hierarchy that says that this is how we use concat classes with Categorifier. And we of course also add the dependency on concat examples in order to get syntactic in scope. So of course this is already defined for us, but to get another view as to like what it's like to define a category, like we saw the very simple case with Haskell where we had just category and arrow. Here's more what it looks like in the in Conal's concat classes library, where there's a lot more classes. They're more fine-grained. In this particular category, the syntactic one, there's not much complexity, right? Each one is basically printing out the name of its operation. But it gives a sense of, first of all, there's a bunch more categories, more than what's on the screen here. Again, more fine-grained. And you don't always need to define all of them. Depending on which functionality you need, you can define ones that are supported by your category or that you need for some reason from the source, the Haskell source code. But this is to kind of give you some example of what that is. And again, if you use commits categories hierarchy instead or some other type class hierarchy, your instance will look different, but it's probably quite similar, really. So we've talked about how this is how to basically convert morphisms from a source category or from Haskell to a target category. But beyond morphisms, we also need to be able to convert types, right? And so how do we do that? Well, the plugin doesn't know about every type you could possibly create. What we have the plugin do is understand a small set of what are called standard types that we can basically map any type into. So standard types consist of things like either, like tuple, unit, void, dict to handle constraints, things like that, not too much more than that. And so we have to define an instance of this hasrep class for each type that says what the standard representation is. In this case, for our type, my type, the standard representation is this nested either, right? Because there's three alternatives. And so there's three alternatives in the nested either. The first one is just an A. The second one is a pair of A and B. And the final one has no parameters, so it's just a unit. And then we have to have functions that convert to and from that standard representation and the actual my type. Two things you might notice about this. First of all, using either and tuples and unit, it looks a lot like generics, just there's no metadata there. Unfortunately, we can't use generics currently. It doesn't inline enough. We need this to inline very strongly, basically. And GHC 9.2 has aggressively inline generics option, which still does not do a good enough job for us. And also, generics doesn't support enough types, actually. Things like constraints, as far as I know, aren't supported. And so we would love to down the road take advantage of generics and not have to use this, but for the time being, that's unfortunately not an option. Uh, but like generics, this is very boilerplatey, right? Like we shouldn't have to write these instances that all do basically the same kind of thing. And thankfully, except in very few cases with JDTs, we don't have to. So we can use a bit of template Haskell, and all you should have to define is derive hasrep for your type, and you'll get a reasonable standard type to use. And so this is all the boilerplate you need in your code when you define new types, that you have to have these corresponding hasreps. And the plugin will also tell you very explicitly when it needs a hasrep that you haven't provided, what type it's for and everything. So, it's pretty minimal boilerplate, but it's still, it would be great to have that derived generic in there instead. So we didn't get everything to work. I mean, we just saw, we had that bit of boilerplate, and we needed to get everything to work, right? So we can't get an oops or any even good error when we're producing the flight controller. We need to get everything through the plugin one way or another. And so really we're compiling almost anything to categories. But what do we do when we can't categorify something? Well, we added 2 loopholes to the plugin. Basically ways to get things through the plugin when the plugin would otherwise give up. The first of these is called native cat. It's a type class that basically allows you to specify an explicit interpretation for a particular function in a particular target category, right? So we used to use this a lot actually in our code. Now we only have one use case left, which is exactly the one you see here. What this instance is saying is that for the function krounddouble in that package, it's a fully qualified, symbol is a fully qualified Haskell identifier. So for that function, when you're categorizing or categorifying to cat, which is our C category, instead of actually running through the plugin and trying to process that whole function, you should just use the result of calling cat on krounddouble. The reason this works is because krounddouble is still defined using our higher kind of data style. So basically, again, like using those type parameters, we can interpret it either as standard Haskell or into our C AST. And so basically, this is just saying like, okay, you called it here with the standard Haskell interpretation, but we're going to return to you the interpretation in that CAST using the old higher kind of data approach. And so this is great if you have some reason why you have like one function that's getting in the way of your project working. You can skip the plugin for it, very explicitly write out what that should look like in your target category. Fingers crossed you actually like get it right and it does the right thing. But it allows you to bypass the plugin when you really need to, when something's in your way. And again, this is something we used to use a lot. We eliminated more and more and more of these calls over time, and it allowed us to have a working system through that whole transition, rather than just dealing with, like, oh, nothing works yet until we can get everything through the plugin. So that's great when you have individual problems like that. But sometimes you have whole classes of things. For that, we have another loophole called automatic interpretation. This is great when you have like a common pattern that gets in the way in your code base. The downside of it is that it does require more knowledge of GHC. You can see and hear that it works with core expressions, and you are actually translating, kind of a kind of function into a kind of expression in the target category. And so, yeah, it is more complicated to work with, but it can solve, large classes of problems or problems you run into all over your code base in one place. So that can be very helpful. We do use this also. Here are some other, but of course, like we think these workarounds are great. They've been very useful and helpful for us. Of course, what we really like to do is patch the remaining pieces so that we don't have to use these things. One of those remaining pieces is existential types. We don't currently support them because type synonyms can't have existentials in them, so we can't define that hasrep type instance, the standard type using for all. One thing we could potentially do is use something like an exist type that hides the existential. But that has kind of cascading effect on the types that are then used within exists, so they have the right shape. forcing us to then support additional types as standard types, making that part of the plugin more complicated. But again, that's one of our open problems. Another is support for mutual recursion. Simple recursion works fine. You can use recursive functions. We have a lot of that. One of the problems with mutual recursion is not only does it fail, but sometimes it fails with non-termination, which is of course very hard to identify. The difference is, like, if it's a local definition like this let bounded one, the plugin will identify it and will tell you like where exactly the cycle exists. But if it's at top level definitions, we can't identify that cycle. And it's very easy for mutual recursion to leak in. Like, this is a simple case of building a record that just works in Haskell, but it has that reference to A inside building the thing where you're referring to another field, and so it causes that loop where you need the value of Baz in order to get the bar out of the A when we run it through the plugin. So this kind of case is easy to work around by pulling out that value and using it in both places. But really, you shouldn't have to rewrite your code in order to use the plugin. So this is a place where you still do have to do that. And of course, there are places where mutual recursion is more fundamental and you can't just easily eliminate it. So you have to, again, have other workarounds. And of course, there are other shortcomings than just these two. For example, like, you can't use IO anywhere in there. And there are others that we know about, but still more that, like, we've covered our own use case, but we're sure, like, as other people have different use cases, we'll need to find and fix additional things. So we haven't really, gotten to compiling anything in categories yet. We made a lot of progress on the shoulders of Conal Elliott and others, and we're looking forward to, fixing a few more of those significant issues. And again, this does currently work to convert our 30,000 lines of Haskell code that, fly a plane into C code that flies a plane. And it's been working well for a long time now on in this project. So it really does work. And so again, it's on open source now. Hopefully, you have some idea of something that might work as a category for you that you could try to use, or uses of Conal's categories. But let me know, like, what you want to use this for. If you need any help getting anything to work, I'm happy to help with any of that. So thank you for listening. I hope it was an informative talk. On the screen now are some of the important links from the talk and contact information for me. And again, I'm happy to answer any questions about this project now or whenever you have them. And again, thanks so much.
Okay, we're live, apparently. I hope that's true. So Greg's with me for the Q&A. Again, if you have any questions, you can just write a message to me. So far, I didn't get any messages, but as I said, we have a stream delay, so we'll probably just wait a few more seconds and then some questions gonna... Oh, there's questions now. Okay. Well, okay, let me just read this very quickly. Kai asks, how does cross-package categorifying work? He would assume that the plugin needs access to the core code of the library, not just the interface. I would assume the same. Can you elaborate on that a bit?
Yeah, that's a great question. So that's true. It needs basically to inline, or as I mentioned, in the case of references, we can like pull it in but keep it in a separate definition. In that case, the easiest way to do that, I didn't mention in the talk, is to basically use fexpose all. Well, now I can't think what it's called. All inlinings or whatever, and that just like will basically, for your libraries that are compiled with that flag, the interface file contains basically inlineable definitions for everything. One thing that's actually, this is a difference with Conal's plugin. you couldn't use that same flag with Konf's plugin, which is one of the reasons you couldn't use third-party libraries, because that flag, fexpose all inlinings or whatever. I wish I could remember what it was actually called. With Konf's plugin, the problem is that gives you all the inlinings after optimization, which often means you're dealing with like low-level stuff or 2 inline stuff to for that plugin to work with, because that Konf's plugin works directly with like fmap and mathematical operations and stuff like that. And if you start inlining stuff too much, you get to primitives that aren't supported or other things like that. So since we kind of went to kind of support arbitrary Haskell like more completely, we could take advantage of that option rather than having to basically add inlining or inlineable primitives to like every definition. So we don't actually have to touch the third-party library code. We just compile it with a different flag that causes it to expose everything.
Okay, I think that answers the question quite well. There's another question by Adam who says that Konf's original work is, as you said, a core-to-core plugin. GHC now supports source plugins as well. Does it help you in any way, or did you look into that? Or does it help
we had talked about source plugins so it doesn't help us because, like I mentioned at the beginning, like core is the most lambda calculus-y, so it's what maps best to this, to the compiling the categories idea. So it's like where things are in the most helpful level. We did try to use source plugin early on because we to kind of deal with the same kind of inlining issue where we would basically prevent various inlinings through a source plugin. So that then when it got to the core, we like knew things weren't too inline for us, basically, that they were at the right level. But again, since we've kind of extended it to support more of Haskell, we haven't needed that anymore. So we've gotten rid of that.
Okay, so no more questions in the chat, but if we have the time, then maybe I have a bit of a question that's further apart from the actual work. But I think Konf moved on to Agda now. As you probably also know. Did you like at any point think, oh yes, Haskell is too constrained in this at this point, and maybe we should follow him or look into that?
I mean, I don't think we really had an option for that. Again, like we just had so much code that existed that we were solving this problem for that code. I think that doing it in Agda would be really neat. But I think that Haskell is so much more widespread that it's very useful to have this for that. And yeah, definitely there are places where there's awkward spots and stuff like that I think dealing with Agda would have fewer of those problems, but I'm sure it would have issues of its own as well. So but definitely for our project, it wasn't really an option since we were just trying to preserve a project. It was pretty awesome again that this project was like a Haskell project to write a flight controller for a plane, because no one does that. So
2 minutes. We have 2 minutes. There's a question that's more of an organizational nature. Are the slides going to be available anywhere afterwards? I think at least if they're not already available anywhere, we're gonna publish them. I think.
Yeah, I sent them to Mike, so they should get published. But also on the last slide, if I can get that to actually come up. There's a link there to this talk. It doesn't have the slides in it yet. It's actually mostly a is it showing the slide in my screen sharing? It's just showing me the front one. Oh, okay, I don't know why it's not showing the right slide. Let me try something here.
Oh, now I see.
Is it showing the right slide now? Okay, cool.
Yes.
Yeah. So anyway, and the first link here, compiling anything to categories, is a repo for this talk. So it has all the code that's used with like that actually, so you can actually run the examples with Cabal and some other examples. And then it doesn't have these slides in it yet, but it has my org mode like outline for preparing this. So that's all in there, which is more, I think, more readable anyway, as like a like almost like a blog post version of the talk. And then the slides will be up there too, but they're not up yet.
Okay, very nice. Thank you very much. I think we are out of time now, and we move over to the next one. Thank you, Greg.
All right, see ya.
And welcome back to talks track number 2 after this short break. This is the last talk before the longer lunch break. Yeah, this is about concurrent programming in Haskell now, with all the good stuff like a quick check, property tests, and just concurrency and Haskell by Philip Kant. He is currently working at IOHK since 2017. He discovered functional programming during his postdoc years as a theoretical particle physicist. And he fell into love with functional programming and especially Haskell during that time, and switched to software development shortly after, I think. So again, any questions that come up during the talk, please post them to me as a direct private message. The earlier you write me, the better I can read your question beforehand and not have to read it during the Q&A. That means we can save some time, and that helps everyone. So without further ado, a round of applause for Philip.
Welcome to my presentation on the Iosim Library, which you can use for testing and simulating concurrent code. The goal that we have is to design distributed systems and also to test them. So let's talk about testing first. What does it mean to test some program? Well, you can view the program as some function that takes some inputs and some outputs. And then testing for correctness means that you have some inputs and you check that the outputs are the ones that you expect, right? Now, when I say inputs and outputs, I mean this in a very general sense. So this could either be just ordinary values, and your program could be a function that produces some output values. It could also mean some initial state, and then your program transforms that state to some final state. And testing in both of these cases means that you take some known input or initial state, you let your program run, and then you check whether the output is as expected, or the final state. Now, basically there's two ways that you can go about that. The most straightforward way is to explicitly construct manually some initial state or some input for which you know the output or the final state, and then run your program and check whether it's correct, right? And that is straightforward, as long as you have some way of knowing what the correct output is besides your program itself. But it is quite cumbersome, because manually specifying all those inputs, you typically do that for like a few cases, but not for too many cases, because it's just some work. And furthermore, it's basically impossible to check for edge cases that you're not aware about, because because you're manually constructing the input values. And so if there are some edge cases, then either you think of them and you know that there are edge cases that you need to test, and then that's fine, or they're not. And then by manually constructing them, if you're not aware of them, then you probably will not include them. So there is a better way of doing things, which is property-based testing, as first implemented in Haskell in Quick Check. And there the strategy is that you randomly generate some sample input. So you write functions called generators that can generate you arbitrary input to your program. And then, because in general you will not know like what the expected outcome is, but you will have some idea of some properties that your program should observe. So something like in a bookkeeping system, money isn't destroyed, or something that sorting functions don't change the number of elements in a list, and these kind of general properties that don't test like the whole your whole program for correctness. But if you think of enough properties, then you can like check many aspects of your program, and you can do so without knowing exactly what the output should be for any given input, because you want to randomly sample the input. Basically, you specify those properties, and then you can satisfy that those properties are satisfied for arbitrary input. And that's quite a powerful concept, because you don't have to think of all the special edge cases. You have to write your generators in a way that they more or less exhaustively probe your parameter space. But that is easier than thinking of every individual edge case. Furthermore, there is another technique called shrinking, which basically says if you have generated like your test data and you found some example that violates one of your properties, then you know you found a bug, right? But you don't know like what exactly the bug is. You just know that like for this arbitrary complex input data, some property is violated. Shrinking now allows you to systematically go to simpler input data and then find the minimal counterexample. And then once you have like a minimal counterexample, it's most of the time it's very easy to like see where the problem lies. So that helps you enormously, not only finding bugs, but only in correcting them. Unfortunately, concurrent and distributed systems are very hard, and they are hard to design. And the difficulty is that unless in a sequential program where you can basically follow a linear thread of reasoning and like follow every state of the program from one step to the other, in a concurrent program it's much more complicated because you have multiple threads of execution. And there can be interactions between those. So you can have some shared state, and then you can't follow just one of those threads of execution, but you have to follow multiple and their interactions. And because of those shared state, and because the timing of those, the scheduling is not deterministic, you can get different results depending on how fast each of those threads execute. So it's quite hard to design concurrent programs. It's even harder to test them because you need to have those different threads running. If they're running on different machines, you have to provision different machines, and then also observing like the total state of the program is more difficult if it's running on multiple machines. And this non-determinism is actually very hard. It's very, very hard for testing because some of those bugs, they don't happen in every run, right? They only happen if the scheduling between those threads is just right. And so that makes it very hard to consistently detect bugs. And it also makes shrinking, so the process of simplifying your input data to find a minimal counterexample, impossible. Because if you simplify your test data and the bug goes away, you never know whether that is actually a consequence of just the shrinking itself, or whether it's just by chance that the scheduling of those threads was a bit different. So, what can we do in order to make those concurrent and distributed programs more tractable? Well, we can try to reduce the complexity via simulations, and that's like the content of this presentation. For example, let's take a communication channel, which is like a simple primitive of a distributed program. You have two computers, and one of them can send some information, so they take some data of type A and send that to the other computer, and the other computer can receive it, right? Can take that from the environment. You can simulate those just via a mutable variable, right? So you can define this data type, you can define this channel of type A, and it has two functions. It has a send function where you send some data, and it has a receive, which collects some data. And like the simplest way of simulating that would be to instantiate such a channel by creating an empty mutable variable, and then the send just puts some data into that variable, and the receive takes it. Of course, that's not particularly realistic, and you can add more realism to those simulations, to the simulated channel. For example, this mutable variable is only a one-place buffer, right? Once you have put something, once you have sent one message, the channel blocks until the other side has read it. And that's not typically what happens in a network, right? So you can use a bounded queue instead. Also, that's basically instantaneous communication, right? You put something into the variable, and at the same time, then the other computer can read it. And so you can, in order to make it more interesting and more realistic, you can model the time delay between those two computers. And one way of modeling that is to say, okay, you have these two computers. They have like a networking device and then some cable between them, some distance of the cable. And then if you want to send a message, the first step is like putting that message through the networking device, serializing it. And then that networking device will block for an amount of time that's proportional to the message size and basically given by its bandwidth, like how much data can process per second. And then once the message is sent, it propagates through the network, and that delay is basically given by the distance. It's just like the speed of light that it takes through the wire. And on the other end, you have the deserialization, where the message arrives, and then the networking interface, again, deserializes the message, blocks while it does that, and then you can receive that message. And by that way, by like having those blocking stages, you can also simulate like sending multiple messages through the same channel, and you will see that there will be contention. So sending like two messages of a given size then takes double the time, or like if you send one after the other has already been started to be serialized, then the delay is a bit less. So that's it's a simple model, but it gives you already some of those effects that you have in sending messages. Of course, you can go even further with adding realism. And like the ultimate thing is building one of those channels using an actual network communication, right? But why would you want to do that? Because the idea of doing simulation is to reduce complexity. And the moment you build a channel using the actual network connection, you have the same complexity as before, right? So why would you want to do that? And the answer is, if you do that, you can treat the real world just as a special case of a simulation. And that in turn allows you to write just one code base and then run the same code either in production using the channel that is built on top of real network communication, or in simulation. And then you can use the simulation for your tests, where it's easier to observe effects and it's easier to run them, it's quicker to run them. And you can run the same code that you have tested in simulation in production. And that's the idea of this Iosim library. So far, if we're doing it like that, the advantages of testing stuff in simulation is that it's easier to run because it's all on one computer. You can observe the global state. But this last thing that was hard about these concurrent programs, that's still there, right? You still have multiple threads. You have this mutable variable and you have different threads accessing that. So you don't have determinism and you can't do shrinking and you can't find minimal counterexamples. And you still have that problem with the intermittent test failures. And that is where the Iosim library helps with. So the Iosim library, it's a drop-in replacement for deterministically simulating like large parts of I/O in Haskell. And it covers synchronous and asynchronous exceptions. It covers concurrency in the style of the base library and the async library. It covers software transactional memory. And it has a simulation of progressing time. It has some event log tracing so that you can analyze your runs and like find exactly what's going wrong. You can find that library not yet on Hackage, so it's part of the repository which holds the networking stack of Cardano. You can find it at this link. And you can find like the Iosim library, which is the simulator itself. And you can also find a package called IO classes, Now what's IO classes? IO classes is basically a type class based wrapper around the Iosim library that basically gives you an interface that allows you to switch between production code and simulated code. So it has these monads like monad thread, which encapsulates something where you can have threads. So you have like thread IDs, you can label a thread. You have then building on top that, you have the monad fork, where you can fork off additional threads. And there's all these functions that you know from IO, like forking another thread, throwing an exception to another thread, killing a thread, these kind of things. And then the instance for IO is straightforward, right? You just fork IO is just fork IO from the IO library, and similarly with all these other methods. But in addition to that, you also have instances for the simulator. And by that, you can write your code, your client code, against these type classes. And then when you instantiate your program, for testing, you can use the simulated IO, and for running in production, you can use actual IO. And that then allows you to run the same user code in the simulation for tests and in production, which is really what you want, right? You want to test the code that you're also running. With that deterministic simulation, you can efficiently run quick check tests and do the shrinking to get those minimal counterexamples that tell you what's really going on, which is really nice for debugging. The simulated time allows you to run the tests really, really quickly. And so you can, if you want to, you can have basically years of simulated time running in your CI tests on every pull request if you want, which is really great because you want to find like these rare test failures. The tracing mechanism allows you to analyze what happens, and you can tune like the detail. You can tune the verbosity of that. You can also do things like fault injection, right? You can simulate disk failures. You can simulate disconnects, which of course you can also do when you're testing things in an actual network. You can also like cut some connections from time to time, but doing it in that framework is really convenient, and you can like tune the rate for these failures in order to find those errors that you would also stumble upon in production after a year of running the system, like probably at nighttime when you're asleep and when the system is under load. And so that's a really nice thing. We've used that to test some of the concurrent code in Cardano. We've used it to test the network stack and the consensus stack. And if you look at the repository and at the issues, we have this label for Iosim discovered bugs. And if you look at that, there's things like fix the asynchronous exception handling, right? Which is really hard to stumble upon in testing because you need to have asynchronous exceptions happening in the first place. And then, or things like resource handling and masking and unmasking. These are things that are like really obscure, but of course they can happen in production. And if you find those tests, those errors that you wouldn't find by just running things in production, it's really useful. So much for testing. Next, let's go to prototyping things. So this is about you have a specification of something that you want to implement, and before implementing it for real, you want to like do a prototype in order to see how it works, how efficient it runs, and these kind of things, and basically validate your design, both functionally and in terms of performance. The example that we're covering here is the Hydra Hat Protocol, which is a protocol for scaling up transactions that are being processed on a blockchain system. Because on blockchains, you make this trade-off between decentralization and scalability, where basically on the blockchain, every transaction is validated by every node in the system, which which basically prevents any one party from cheating and from getting control of the system. But it prevents you from just adding more computers in order to process more transactions, because they're all supposed to check everything, right? So in these layer 2 solutions, what you do is that you process some of those transactions off-chain. So you take away some money from the chain, and then you have like a smaller group of computers that basically send transactions between themselves and agree on some final state that is then committed back to the chain. And so instead of like posting all those transactions to the chain and having them verified by all the nodes in the system, you get some local consensus on the resulting state after those transactions, and only that is committed back. And in the case of a Hydra Hat, that is basically the way of getting consensus is that if one node wants to post a transaction, it sends it to all the other nodes, collects like signatures back in order for those nodes to acknowledge those transactions, and then wraps them up in like one object that contains all those signatures, sends them again to all of them, and then once that with that object that basically says all the nodes agree that that transaction should be valid, then any node can basically go and decommit that and post that resulting state back to the chain. Now, we want to simulate such a network of node, and we want to make a few observations. In particular, we are interested in the performance of the system, and that means we want to know the settlement time. So how long does it take from sending the transactions to the peer to getting that object that says, okay, everyone has acknowledged that. And we want to know the throughput, like how many transactions per second can the system handle. Of course, that depends on a number of parameters, right? It depends on the networking infrastructure. So it depends on the bandwidth that these networking interfaces have. It depends on the transaction size, because that basically tells you how much bandwidth you need. It depends on the distance between, so the geographical setup of those nodes. And also it depends on like the concurrency, in the sense of how many transactions are those nodes willing to have in flight at any given point in time. Because if you have more transactions in flight, you can amortize some of the latency by sending basically more messages before you wait for a reply. And then of course it also depends on like the CPU and processing power of all those nodes, because they need to do transaction validation and perform and validate signatures. We have like looked at how to simulate those communication channels already, and then we also need to look at how do we simulate like those things that take time on the CPU, like transaction validation. For that, we introduce a data type called delayed computation of type A, which contains the result of the computation, and it contains the time that it takes to compute the result. With that data type, we can define a monad that tells us how to do like those kind of delayed computations, how to chain them together. So for instance, if you want to have a delayed computation that depends on the result of another delayed computation, like here, you have some delayed computation and you want to put that into a function, another delayed computation f, then you can do that by basically looking at the result of putting x into f and the time that it takes to do that second step in the calculation, and then the overall delayed computation just is the result of that second computation, and it takes as much time as those two things together. And similarly for those other, for just doing one computation after the other without using the result, and for doing delayed computations that don't depend on one another. Then you can run those within any monad that basically has a method, a way of delaying for some time by just doing that delay and then returning that result. And Such a monad is also implemented in the Iosim and Io classes. So that's the monad timer. And then for I/O, that's just a simple thread delay. And for the simulation monad, that is basically just adding some number to an internal counter. With that, we can now simulate a node in that Hydra system. So we basically have two communication channels. We have one for receiving messages, and we have one for sending messages, right? And those handle basically all the communication with all the other nodes. In particular, when there's multiple messages coming in at the same time, the networking interface will like block on the first one and only start processing the other one once that is finished. Then you have like a queue of incoming messages. You have like an event handler for dealing with all those protocol messages. And then, for example, if you're asked for a signature, you do a delayed computation, you produce the signature, and then put that message with the signature into a queue. And on the other end of the queue, you have again a networking interface that takes these messages that are prepared one by one and sends them to the rest of the network. Right? So that's the idea. And then again, like you have those networking interfaces blocking upon serialization or deserialization. You have just basically sending it. The time that it takes depends on the distance. And then you can set up a simulation where you fix the geographical location of all the nodes, you fix the bandwidth of each of those networking interfaces, and then you also say like what's the message size, how many of those transactions are the nodes willing to have run in concurrently. And then from that you can run these simulations, and you can create graphs and that's like only based on the simulation before you start the effort of actually implementing that for real. And if you look at the results here, so you have different panels for the number of transactions that the nodes have in flight at a certain time. And then you're on the x-axis, you vary the bandwidth of the networking interfaces. And then here you see the transaction throughput, like how many transactions can you handle per second. And then you see if you have like insufficient bandwidth, you're limited by that. And if you increase the bandwidth, at some point you're saturated. And then you are in the region where basically you are limited by the round trip time between different nodes. Now, if you increase the concurrency, basically you try to have multiple transactions validated concurrently, you can amortize the latency between those of the round trip time, and you get a higher throughput. But at some point, increasing the concurrency even further doesn't allow you to increase the throughput, and that's because then you start being limited by the processing time of each node for like creating those signatures and validating them and validating the transactions. And all of those effects you can see in that simulation, which is fairly simple to set up. You can also see like trade-offs that you have. If you look at the lower row, you see the confirmation time for a single transaction. So that's the time from sending a transaction to the peer nodes and getting back that object that basically contains the signatures from all the other nodes with which you are able to then basically post it back to the chain whenever you want it. And you see again that increasing bandwidth decreases the confirmation time. But you see that if you increase the concurrency, the confirmation time actually goes up, and also here the spread goes up. And if you think about it, that is not that surprising, right? Because if you are trying to get multiple transactions validated at the same time, or get consensus on multiple transactions at the same time, then the chances of like the networking interface being busy at the moment that you send a transaction, those go up, right? If you're only processing one transaction at a time, then the network interface is free most of the time. If you're trying to send multiple at a time, then you are bound to like run into a blocked device sooner or later, and that gets worse if you increase the concurrency. And actually here, because of the log scale, it looks like the spread would be lower here, but that's only an artifact of the log scale here. So it's also the spread that goes up, right? Yeah. and in particular, you see like these are like so in the simulations we could have introduced like an explicit randomization of like how long it takes to send one transaction through the network, but we haven't done that here. So all the spread that you see here is just because of the blocking and these contention effects that we have in the simulations. So it's quite a it's a fairly simple simulation, but it's already giving you so some of those interesting effects. To conclude, you can use that Iosim library to test concurrent code in simulation, which allows you to test much faster, so you can get more effective test time in a given like wall clock time, and that allows you to run much more tests in your CI. You can also do the kind of fault injection that really makes those tests more valuable, and it's deterministic, so you can get those minimal counterexamples via shrinking. One thing I haven't mentioned is that recently we also added, we had John Hughes suggest and also implement a mechanism for reordering some of the scheduling in order to like not have just one ordering of those threads, but to find like reorderings of threads that are racing against each other, and then also find some permutations in the scheduler in order to just cover more, but not like try to find every permutation, which would be exhaustive. And with that you can like have the benefits of running your tests in simulation, but having still the same code run in production with those wrappers, with those type class wrappers. And you can also write that library to just write quick prototypes. And because of the timing that you have in the simulation monad, you can also predict the performance and get some performance characteristic, not only like the functional correctness of your algorithm before you do the full implementation. Thank you. Do you have any questions about that?
Okay, so we're back to the Q&A together with Philip. Hello, Philip. Thank you for your talk.
Happy.
So a Q&A is based on questions. So if you have any, you should ask them via direct message. Post them just to me, Markus Schlegel, in the Gather chat, which is a bit hard to use, I know, but I think you can do it. So if there's no question, then my first question would always be just, is there anything you want to elaborate on that you, like now watching your own talk once more, you noticed that maybe you wanted to go into a bit more?
I actually haven't really watched the talk because
so there's not maybe,
so,
yeah, but maybe I have some questions, or not maybe,
Mm-hmm.
but I do have, but I would prefer others. So there's one. Okay. Does it make sense to take a code base that uses polysemi and write an interpreter using Iosim? Have you looked into polysemi yet?
No. What is polysemi?
That's effect library, I think. Very, very high level description.
I mean, it depends on like you might. I mean, if polysemi is using I/O directly, then you might have to change the wiring internally so that the library itself would use I/O classes, and then you could do that. And yeah,
I think I'm by no means an expert on this. I know my coworkers use polysemi. I think what it does is it allows you to write your own effects. Like you could write an abstract effect, like something like a
okay.
delayed computation, and then you can provide different interpretations of that.
Yeah, and then I think you should be able to plug it in there, and then basically write your effects based on I/O classes, and then either perform them in simulation or for real.
Yeah.
That should be.
Brian asks, are you going to put this on Hackage soon?
I think we should. Of course, it always takes time, and there's always lots of things to do. So it's something to to ask for prioritization and to do that. But so in the past, IO has put some libraries on Hackage, and so we have one for basically ensuring that there are no thunks in your code. So the no thunks library is something that we put on Hackage, and this one would be like a great candidate because it's pretty useful. Yeah. So we don't have it on Hackage yet. I hope we'll find the time to do it. Otherwise, you can clone the repository and take it from there. There's also some. One of the things I didn't really get into detail on in the presentation itself is that we're also looking at this thing where you don't want to test only for like one possible ordering of the threads, right? So the partial order reduction where you basically look at different variants of the scheduler. So you look at threads that are like racing, and then you reorder those schedules a bit. So that's something that is under active development, and so maybe we'd want to like wait for that to be finished before putting it on Hackage.
Okay. I understood that you already did that via the quick check stuff. I thought that you used quick check to generate different traces of the program execution, right? But that's not the case then.
So for quick check, you can like you generate different different events in your program, and like different different. If you're testing networking code, you simulate different things happening that your nodes interact with. But internally, the scheduler of your internal threads that basically runs in the deterministic simulation, so that it doesn't like change and some bug disappears when you change the input data. But then this next step is like looking at a few variants of the internal scheduler as well. And,
that's actually quite a huge area of research still. Because you mentioned shrinking, right? And shrinking these different execution paths is very non-trivial.
So. I was talking about like this in passing in another presentation at transfunctional programming, and John Hughes was the chair, and he told me afterwards that the deterministic scheduling is probably not the best, that you want to have some variation in there. And so he's provided some input there and added that. Yeah.
All right, let's have a quick look at the questions. I think there's no more questions from the audience, so that means I think we're also running out of time anyway. So okay.
So you also had some questions, you said, or?
Yeah, maybe you already answered it. I think it was just about the quick check, how exactly it fit into the different traces that you used. Or maybe I have to look at my notes. Okay, maybe the delaying of the computations, that's only relevant really for simulation, or is that also correctness and safety?
So I mean, it is for like so the thing where I used it in the simulations is for predicting performance, because you want to have the delays, and you want to look at how long something takes, and for that you need to like explicitly keep track of like how long stuff takes. Yeah, and then of course there's also like, and it uses the simulation of like putting threads to sleep and waking them up. So that is included in the simulation of the scheduler. And this delayed computation data type is only making use of that via the thread delay. Yeah, in order to predict performance. But you can also, like, if you're simulating things, yeah, where the threads, like, we have, for example, timeout, waiting for some messages, then it's also, then you use that same mechanism, but just to simulate a node that's like waiting for something to happen on a connection before it times out.
Okay.
So then it's also for the functional correctness. Yeah.
Then again, thank you very much for this nice talk.
Thanks a lot.
And we're gonna move into the lunch break, and we'll see you at, I think, 2:15 on this track at least, or no, on all tracks 2:15, but on this track with specification-driven design by Joachim Breitner. Yeah, nice lunch break, everyone.
Thanks.
Hello, everybody. I hope you had a great lunch. I said it already. Please mute your microphones. Another thing, how we do with a Q&A, please find me in the chat. My name is Bianca Lutz. I just made an announcement right now. So look for me and message me directly, whatever it is that you want me to relay to Joachim. And then we will address, hopefully, what you are interested in. If you don't supply any questions, then you have to live with whatever I can come up with. I'm not sure that's too interesting. So, so much for the pretext. The interesting part, the reason why you are all here, Joachim Breitner telling us something about specification-driven design. I'm actually not sure how much introduction Joachim needs, as he's, I think, quite often at Konf. He's quite active in the Haskell community, as I learned. So probably most of you will know him. Anyway, I didn't, so I went to his webpage and rummaged through his blog and his publications and found an awful lot of awe-inspiring stuff about GHC, formal verification. Sorry. So I would say, like, he is just the guy that we want to talk about specification-driven design. And in a moment, he will explain to us what this idea is about, but not really as from a theoretical point of view, but really backed up by real-world experience. So you can expect quite a number of concrete, I'd say, implements on how to really use this approach to get your software project the way you want it to. So if this was on premise, I would ask you now to give a very warm welcome to Joachim. Obviously, you can't do that, so I do it on your behalf. So here is Joachim Breitner.
Welcome to this BobConf talk. Thanks to the organizers for having me. And it's a pity to have to do this pre-recorded, but I hope it will still be as good as the live experience, or at least close. So before I start, I want to manage expectations a little bit. The following talk is anecdotal in nature. So the thing I'm going to be presenting now is not just an idea that I had and haven't tried in practice or anything like this, but it's also not a full fleshed out philosophy that you may be able to directly apply to whatever you're working on. It is a real experience I've had working on a real production system, and I think it's worth sharing. Also, there isn't really probably not much new ideas there, in the sense that there are existing complete fleshed out philosophies of how to design systems out there that this is probably just one aspect of and one variation, and I don't claim novelty here. But still, I hope you can take something out of this. So here's the setting. Imagine maybe you're part of a startup. Some visionary founder has a really great and innovative idea for something that the world hasn't seen before. Or maybe you're just reinventing the wheel again, but you have good public relations, so the whole thing flies. And so you as the founder of the startup, maybe you probably have many ideas about how to build a thing. You have some idea for a secret sauce that makes this better than anything else. And you gather a bunch of 10x programmers around you, everyone an expert in whatever field you need to build the thing you want to build. And they're all very excited to build the thing you want to build and contribute to this machinery that makes this great. And they all go out and go off and build this thing. And the whole thing grows and grows as you add features and as you add new ideas. And at some point, you think you're done, and whatever you have grown and built, that's what you ship. Great, well done. But what could happen is that as you build the thing, it kind of grows, and when you're done, whatever shape that thing has, that becomes the interface, the exterior view onto the system or platform or service that you built. Which means it's defined by how it was built. Maybe the names and types and shape, like and the functions of the interface kind of reflect the interior workings of the system. And maybe that means that your users will have to understand how the system works in order to use it. but maybe they don't want to. Presumably, they just want to know what your system is, what it does, and how they can use it without needing to know the interior of your machinery. Also, when you build it like this, then maybe the whole behavior of the system, so not just how you interact with it, but also what happens then, is purely defined by how you build it. Now that's implementation defined. And that may be good, but it also means it may be hard to now evolve your system and change it, because you don't know what behaviors maybe the users now rely on, which behaviors of the system are just now part of the contract with your users, so to say. So all in all, clearly not so very satisfying. And at my previous job, I think we were at risk of doing precisely that. So what we were building is what I would describe as a decentralized serverless service hosting platform. So from the user's point of view, or the developer's point of view, you can create services, you build them in a language that compiles to WebAssembly, which is this nice container or nice abstract format for compiled code that can run in a sandbox very nicely. You upload it to the platform, and then it can interact with the outside world and also with other services on the platform using asynchronous messaging. So there were quite a few things we were building that didn't exist in this particular format before. And at some point, I vaguely remember that the team building the system component that passes messages between these services and between the shards and whatever that means, they were claiming we can now support messages between services, and we didn't even have an inkling of how these services would send messages or receive messages, or how the outside would send messages to and from the system. So my impression was that we were at risk of treating the public interface of the whole system as an afterthought to implementation. And we were building it without knowing whether it makes sense end-to-end, whether it's usable, whether it's understandable for our developers. And in a very abstract sense, we were building it without knowing what it is. Furthermore, we had other people that were supposed to build on top of the platform that we're building. They were building tooling, development kits that compile to this kind of service module. We even built a new programming language. That's how I ended up in that place. And of course, these developers, they need to know the interface of the system and how it behaves. But if you're just building it from the inside out and then define the interface by accident, more or less, and then build on top of it, then we have a very long critical path. So we could not start building on top of features before they were completely implemented. And that could be improved. So at that point, I started making a little fuss and annoyed the relevant people enough to let me go ahead with this idea that I proposed of nailing down the public specification. And the idea that behind this is that we should think of the system from the outside. So for a moment, let's try to completely forget all the clever implementation tricks and focus on the what, not the how of the system. So what do your users need to know about the system? Okay, so surely the concrete interface. So for a network service, that might be the wire protocol, like the bytes on which order and what they mean, everything. For web service, might be the REST endpoints and arguments and results. For library, it would be the function names and function signatures. But the interface isn't enough. The users also need to know what it means to call a certain function, to invoke a certain entry point, how they interact with each other, how time plays into play here. So more fancily, what the semantics of the system is. So how do we describe the semantics? Isn't this already the how question? Like, how does the whole thing behave? The best question may be best answered by implementation. Well, as I said, that you can do that. That's possible. But then you have an implementation defined system. And maybe sometimes that's fine. But sometimes I think we can do better. And the idea is that you only describe what's really relevant to the user to use your system. and ignore as much as possible of the stuff that the user doesn't care about. There are different forms the specification can take. So it could be just a bunch of text, a bunch of prose describing how the system behaves, and that's a good start, of course. Or you could try to be more formal and describe the behavior of your system with mathematical precision, or at least some approximation thereof. Some pragmatism is probably always needed. So you could do by starting to describe the state of the system with mathematical notation, like sets, maps, relations, lists, all of it. But describe the abstract state. So not necessarily how your file system internally stores the data that the user gives you, but rather what is the mental model of that. And in the end, you get a document that is, in principle, everything a user or developer needs to interact with your system. Everything they need to know should be in there, from the very concrete details of the interface, how to encode the messages, what is the parameter list of a certain function, and so on. But also what it means to use them, how do they interact, what are the preconditions, what are the failure conditions, and so on. And conversely, anything that is not in the document, anything that the user does not need to care about should not be in the document. All the things you do behind the scenes, things you do about crash recovery, decentralization, performance, scaling, security, access control maybe for administrative purposes, logging, whatever. All the things that make your product great because it works so good, but doesn't really affect the raw essence of what it means to be your product, they should be out of this document. So this was the idea that I set out to establish, and after enough nagging, I got some encouragement, and I set out and I wrote this that specification document for our system. It was actually initially called the public spec, because not because the document was public, because at that time it wasn't public, but because it describes just the public, the external view onto the system. It has been published since. It's now called the interface spec, because the public spec was too confusing. But I find that name still a little bit misleading, because it's not just the interface, if you think of interface as list of functions and methods, because it also contains the semantics. And in this document, I actually described the semantics twice. So there's a prose-oriented section that describes but still very technical, but accessible way, all the entry points, all the methods, and then with prose describes what these things do. So it looks like a reference document manual maybe. And then there's also a separate section which is more rigorous and more mathematical. So there I start describing the state of the system as an abstract mathematical object. So it has a bunch of fields, and each field is a map or a set or a list. And of course, this is not the state that you would see in production, because production that's distributed, there's a lot of other stuff going on. But really, this is what we think all that a user ideally should need to know and think about when interacting with the system. And I think already this section makes the work on a document like this worthwhile, because you're really nailing down a abstract, more conceptual model of your system that separates the what from the how of the implementation details. And once you've described the state of the system in that way, you can, for every state transition, for every function call, for every entry point, for everything that interacts with the system, either from the outside or maybe from inside, from one of these services, you can now say how the state gets transformed. And that could either be a function that takes the old state and returns the new state, like if you want to do it more functional programming, or it could be a predicate that describes if the state before had these properties, afterwards it has these properties, which is actually quite versatile, because it means you can easily describe non-determinism or underspecification. because you want the specification to describe the behavior with enough detail to make sense for the user, but probably you don't want to over-constrain it in the sense that the implementation might have to make certain choices about scheduling of different events. Because of distribution, things might happen. There might be resource limits, there might be failure, and all of these things allow the one implementation of the specification to maybe vary a little bit within clearly defined bounds in how they behave. And a modeling using a mathematical idea of the state, but then a relational description of the state changes actually works quite well. So the document grew quite a lot. It is now almost a book. It actually is a book because when I left, a colleague actually printed it as a book, which I found very, very nice. Thanks, Hans. And it's certainly not the most accessible document, but it doesn't have to be. So it's not meant to be a tutorial for somebody working with this ecosystem for the first time to fully understand everything, because it's also not a place for, or I think it's not a place for long justification, long design decision, history, a place where you would document alternative ways of how you could do things and describe why they were done like this. So I tried to keep it very concise and precise, and a reference manual for people who mostly know it already, but they need to have it written down somewhere. And even with that restriction, it still grows because these systems just become very complex over time, even when they claim to be very simple. I wrote this document in a text-based markup language. We used AsciiDoc because we used it elsewhere. And the point for that is you can actually treat it like code. You put it in a Git repository, and when you make changes, you make pull requests, and you can review them. And this allows you to have a engineer-compatible model of communicating around this thing. And actually, as I said earlier, we have people building the thing from the inside, and we have people building on top of the whole thing, and we have the interface in between. And by introducing this document and also the repository around it and a workflow where new features will be fleshed out by describing their changes to the interface, separately from thinking about how to actually implement them, we created a forum where the people can come together that use the interface from both sides, the people building it and the people using it. And they could now argue and discuss and debate and refine and improve on more or less equal footing. And I think this also helps a lot to build a nice interface and build a system that has a nice exterior view. Because otherwise you might fall prey to Conway's laws, which says that your software always looks a bit like your organizational structure. And more concretely, I observed, I mean, it's not very surprising, there's always a tendency to push complexity into other layers of your system. So if the people building the system, the implementation, get to define the interface, they're more likely to push complexity across the border to the other team. And maybe build interfaces that's very low level, that may be very much tailored around how they actually build things internally. And it may end up being hard to use or tricky to use, or it may not be abstract enough to stay the same interface as the interface changes and evolves. So by looking at the interface on its own and discussing changes there, you have a better chance of thinking, couldn't we phrase it like this? And then if we ever do this particular feature, then we don't have to change the interface. As you could imagine, it took a little while to anchor this document and the process around it in the organization. And I think it stays a continuous struggle to keep everyone on board, because of course this kind of slows things down. If you just get, like, somebody from higher up tells you, now do this, we need to get this done in 2 weeks, and now you have to sit and write a document and discuss with people who get to use the feature first how this actually should look like, and then get to implement it. Yes, it slows things down a little bit. And there's always the risk that this kind of will fall on the wayside and people will just fall back to just building new features and maybe later update the specification document with what they have actually built. And then it just becomes documentation. And this risk exists, and in order to counterpoint it a little bit, I, at some point later, suggested that we maybe should invest into a reference implementation to make it more concrete. So what does this mean? So the idea behind the reference implementation is you take the specification document, and then you build the most simple, most elegant, and most direct implementation that actually fulfills the specification without looking at the concrete production implementation. So you basically like clean room re-implementation, and you make it as simple as possible. So you ignore everything you can ignore while still sticking to the specification. You ignore performance, reliability, scalability, persistence, crash recovery, distribution, security, all of the things that make your production system great, you can just ignore. But you still want to fulfill the whole specification, not just build a model of it, but really fulfill it, including the concrete interfaces, so that suddenly now you have two implementations of your system, or of the idea of your system, of your specification. And both are kind of real enough to be used by the tools and libraries and programs that build on top of your platform. So now the people building these tools can now test against both production and reference implementation. And everything that something doesn't quite work, you can now compare behaviors, and this will hopefully turn on all the spots where the production system is not behaving as the specification. So every time there's a difference in behavior, it's either a bug in one of the two implementations and you can track it down, or maybe it's just a bad formulation in the spec and then you can fix that. So this really helps to keep the production implementation honest and close to the spec. And when writing this reference implementation, my suggestion is to really resist the urge to share code with the production implementation. Because once you share code, any kind of bug or misbehavior that is in the shared code will not show up. And a good way to do that is, of course, to use a very different programming languages. So we used Rust in the production implementation, and then when I set out to build the Haskell, the Rust implementation, I used Haskell. We had the spec maybe for half a year, and things were going okay, but not great with like sticking to the spec. So I just did this thing. I sat down and re-implemented the whole spec in Haskell. And Haskell is great because it's really, I mean, you've heard this probably a few times before, it's really great for rapid prototype. I could alone in a few days implement the spec as it was at that time, and it was actually working compatible with the systems that were building on top of our system. There are plenty of libraries to use, so all this plumbing I needed to do for the interfaces, like HTTP, CBOR, crypto, WebAssembly stuff, I could just use libraries for, so this was great. And then because it's a very high-level language, I was able to mostly separate the plumbing code, so the code that deals with file formats and networking and these things, from code that ideally in a very high-level way reflects the specification and not just the specification. So ideally it should just read like the specification document, or at least the mathematical part of it. And well, now that we had the teams that were building on top of the platform, now they could use two separate implementations in the test suite, and this helped to find bugs. It also just gave them more confidence in complaining when the implementation didn't match the spec, because they could say, well, with your test, it passes here, it doesn't pass with your code, please fix it. And previously, it was more like, well, look at this document there that somebody wrote, but maybe it's not up to date, and so on and so on. Okay, and now that we started writing code around the spec, we can actually go one step further and write what could be called a specification acceptance test suite. Again, this is code written with just specification in mind, but now it sits on the other side of the interface. And it uses the system, according to the interface and probes it in all the various ways to see if it actually behaves like the interface describes. And again, we have benefits of using an expressive language like Haskell with maybe good testing libraries. So we can do extensive fuzzing, we can do property-based testing, we can do just very quickly describe many different test cases because it's a rapid programming language. And because the test suite is based on the specification and not the actual implementation, it is compatible with both implementations we have, the production implementation and the reference implementation. So you can use the test suite to test the reference implementation, which is already useful because it's not much fun to write code without being able to test it easily and in isolation. And then the test suite can also be used to test the production implementation, and maybe should be part of the CI system for the production so that you continuously check that you're still satisfying the spec in at least those ways that you could map and express in the test suite. And then in the end, you have these two specification-derived artifacts, the reference implementation, the reference test suite. They can test each other, and they can test the production implementation and the production tooling on top of the system, so like crosswise. And this gives a very nice confidence in that really everything you build is nicely built around the spec. So in my case, the test suite ended up being quite substantial, more than 400 individual tests. And indeed, it was very great to use Haskell there because just 1 or 2 lines of tests could easily express something that in the previous tests we were writing, maybe with Rust, were 10 lines or 15. And one thing I'm particularly proud of is that I introduced what I call the universal service. So one problem with testing a system like this is that for many kind of test steps, you want to interact from the outset with the system, and then in the system there's some kind of service running and it needs to send another message to another service and then comes back and then responds, and some complex interaction involving both the outside and services on the platform. And if you just do it pedestrian-wise, you have to program these services individually using languages you have available, and actually very early we were partly writing them by hand in raw WebAssembly. This is like almost writing machine, well, not quite machine code, but it's very tedious. So it doesn't scale. It's a lot of work for a simple test that maybe just sends a message back and forth. So what I did instead is I wrote a simple canister that implements a very simple programming language that can instruct the the service to perform certain steps in sequence. And it takes the steps to perform from the message it receives from the outside. So I can write a test that sits on the outside and then sends a message into one of these services. And the message contains some bytes that tell the service what to do, send another service, which again sends another message, which again tells that service what to do, or maybe respond, and all the other things a service could do on our platform. And then I embed this in my Haskell test suite by a simple DSL that allows me to describe in Haskell both the behavior of the test runner outside and completely transparently in one line and no separation what happens on the service. And then under the hood it takes this DSL, creates a very simple script language out of it, passes it in the message to the service, and the service executes it. It's actually simpler than it sounds. But it was very productive because now complex interactions are just 1, 2, 3 lines of Haskell that I don't know how we could effectively do otherwise. So this is roughly as far as I were able to push this development model in practice. If you want to go further, there are some ideas of things that I would want to do but didn't manage to do. So at some point I was hoping that the reference implementation, the nice, carefully polished, abstract Haskell code that I wrote, could be the specification. That I could take parts of that code, the relevant code in the non-plumbing modules, and include it in the specification document just the way I include this kind of ad hoc pseudo math right now. And I think if with a little bit more effort and care, this might be possible. It might be more likely possible in a language that gives you more control over syntax, because you want this not to look like Haskell, because not everybody likes reading code that looks like Haskell. You want it to look like pseudocode that any reader is supposed to at least make some sense of. And languages like Acta with the mix-fix syntax, or maybe Isabelle with this very flexible way of pretty printing the code in LaTeX and allowing you to replace certain definitions with actual LaTeX macros, might actually be a way of getting very nice output there. For Haskell, I think the main reason why I gave up was that record syntax is just ugly, especially a nested record update in Haskell is not a simple one-line thing. So you either need lenses, and then you have these operators that are not obvious for non-lens developers, or you have these manually written nested record updates, and then it's not pretty. And then clearly a more ambitious goal would be to take the artifacts that we described above, so the specification with its mathematical or pseudomath content, the reference implementation, the reference test suite, maybe even the production implementation, and then connect them all using formal methods. And in the end, have a formally verified implementation of the whole system. Now, this kind of extreme goal, that's something you can do if it's like a big research project or a very big commercial thing, like things like SEL4 and Composable. They have done that, but it's still out of reach if you just want to build a thing and ship it. But it's a spectrum. You could start maybe taking the math in the document by hand translating it into a theorem prover, so you have a formalized model of your system, and then prove certain core properties about your system, like some safety properties that this canister cannot change the code of the memory of canisters are our services. This service cannot change the code of that service over there, or stuff like that. At some point, I even managed to take the Haskell code from my reference implementation and convert it into Coq code, so that I could load it in Coq and could start proving things formally about it. So this would be one way of obtaining a formal model without having to write it again. Just take the reference implementation code and convert it into a system where you can do formal reasoning. But then I didn't really get to do much with it, and the code has grown a lot since then because the system grows. So yeah, the practicalities of getting something shipped seem to be hard to getting in the way of doing these kind of formal proofs. And there's a pity, because if I could have ticked off that box, then what I've just described would almost completely fulfill the requirements for a deep specification as termed by the DeepSpec project. The DeepSpec project I have to check, a large research project in the US with a few Ivy League universities, thinking about how we can make these kind of software specifications better and how to integrate formal methods. And they have 4 requirements they have for a specification to be what they call to be maximally useful in their opinion. So it needs to be rich. So rich means it's not just the interface, but it also describes the complex behaviors of the system. And in a way we have that. Our specification document describes how the system interacts upon certain messages and interactions. The specification would be two-sided, meaning connecting both implementation and clients. And in a way I could argue we have that because we have not just the reference implementation built in the spec, but also the test suite that deals with the spec from the outside. Has to be formal, written with proper mathematical notation. And we're halfway there, so we have this mathematical notation, but it's kind of ad hoc. It's just on paper. It's not something that a tool can consume to make things with it, like formal reasoning or generating code from it or stuff like that. So here we are falling a bit short. And then the fourth requirement is it needs to be live. and live means executable, and we have that in a way because we have the specification not just on that paper, but also as an executable reference implementation. But they also require lives to be connected by formal proofs to the implementation. And of course, this is a big gap that we have where we have these testing mechanisms and reference tests and everything, but still, whether the implementation actually matches the spec and therefore fulfills the properties that we could prove about the specification is not connected because it's still missing this formal proof stuff. All right, as I mentioned in the beginning, little of what I said here is really new. So if you want to maybe read something more structured about a methodology based on something like this, then certain terms you can look for are consumer-driven contract testing, specification by example, domain-driven design, and there's actually a nice talk about Nicole Rauch's idea of functional essence, which also is quite similar to what I described here. So what can you take home from this talk? I think the most important takeaway is that as you design and build a system or a service or something like this, try to picture it from the outside. Create a mental model that is independent of the interior of your system, of the implementation, and is more abstract. And then build your system from the inside out to fill this abstract vision, rather than the other way around of building first and then looking at what you have. So with that, I thank you for your attention, and I'm looking forward to a lively and live Q&A session.
So thank you very much, Joachim. A very, very interesting and inspiring talk, I think. Unfortunately, nobody asked any questions, so we are just left with whatever we can come up with. So I'd say we just start talking, and if anybody has something to add and to ask, please chat me, message me directly, and we will incorporate them. So I think because it was a very concrete hands-on talk, I want to start with a concrete hands-on question. What I was wondering about is you told that this Git repository you had for the specification was acting like kind of a forum, I think, for discussion about the specification. Maybe you can a bit more describe how your actual workflow looked like, where how many people worked on the actual specification, where the discussion took place, stuff like that, maybe.
Right. So this is always a little bit in flux because, of course, not everything, it's not like the whole organization is rotating around this one repository. This is because I wanted this to be this concrete thing that at least where the interfaces and the API is down to all technical detail, it was too detailed for like the high-level design decisions and high-level roadmap decisions. So that happened somewhere else with different people, mostly different layer in the org chart. And usually at some point it was clear, okay, this is a feature that we really want to do, that we really want to do soon. And that's when somebody, that often was me, but not always, would start fleshing out the details and create a pull request against the repository, ideally referencing any kind of other documents, design decisions, meeting minutes, whatever is there, where the high-level goal was stated and discussed. And I guess those people who were involved with the components directly adjacent to this interface would mostly monitor this repository, so they would find out about this discussion or this pull request, and would just jump on the pull request and start making comments and yeah. But as I said, this was partly the ideal thing. Often was the case that implementation already went ahead, and there was maybe a prototype or an experiment, and this turned into the production thing, and then simultaneously with the implementation, the pull request against the spec was great, which wasn't bad either, because it meant you learn something while building it, of course, and that could influence back the spec. So it's, I guess the word isn't out yet whether it's better to decide on the thing, on the specification completely before even doing the first line of code, or doing a co-development between the production implementation of the feature and the spec, and then when you think you know this is actually working, and that's when you merge the specification and say, okay, no, we're not trying to change the thing, and that allows then the people building on top of it just to go ahead.
Yeah, some kind of more evolutionary process where you really like have the spec influencing the code and vice versa. Like, okay.
But it really boils down to keeping the people on board. Like, this is if the engineers implementing the thing, or the engineers building on top of the thing, or the managers feel like this is just getting in the way, or they don't get their voice, then the whole thing just falls apart. So really, if it turns out that you want to be more strict about nailing things down before doing work, then do that. And if you notice that, no, this is slowing people down, and they really want to make progress, even at the expense of maybe changing the implementation after they learned that maybe the other side want to have something slightly different, then do that and keep refining. So we changed this a few times. We tried to introduce some process, and it didn't quite work. And you can tell it doesn't work because nobody follows it.
Yeah. When it gets
to stop pretending that this process is there.
Yeah. Okay. So thanks for that. Now I have one other aspect that is more theoretical, because what I thought was very, very like promising, and oh my gosh, that is nice, was your outlook to how to kind of push the envelope and go in the direction of really formal verification. And oh no, I think we have a question.
No.
I just no, it's not. Oh no, it's just like okay. I just read it. My understanding is that spec-driven design is somewhere between behavior-driven and API-first design. BDD specs can be written by POs but aren't executable. APIs, like an open API spec, are more easily executable but can't be defined by POs. What tools or formats are available to enable POs to write an executable SDD specification document?
Was this question by Nicole Rauch?
If it was by Nicole, then she doesn't appear to use her name, so I don't think so.
It is most inclined to say if it wasn't by Nicole.
LZ101010. I don't know.
I know that Nicole is much more knowledgeable about like what else is out there and these things. So if this was like the room, I would just say like I'll defer this question to Nicole, because I know that I don't really. I like to make things up, as you might have noticed. But I put a disclaimer there. I'm not claiming that this is not just recreating something that exists before, or just another point in the design space for the processes. No, so
But you can. I mean, you can just refer to Nicole. She is on the conference, so
So I think
just look for Nicole. You can,
Nicole.
Maybe she's the right one. And we have another one. Actually, another question. What did you use for your acceptance testing?
So that was Haskell with Tasty as the test runner, and and despite using Haskell and Tasty, it turns out that at least for the acceptance testing, it was mostly like simple unit tests where like I do one single behavior. So I didn't need much on top of Tasty, or I guess HUnit as the thing that propagates test failures out. So we didn't do much fancy things with quick check or small check or something. I guess we could have. It just wasn't very immediately urgent for what we wanted to achieve, but definitely could be done. But yeah, Tasty as a test runner was a good start.
So I just hear from our director that we actually filled the 10 minutes Q&A.
Already? That was quick.
Yeah, that was quick. But I think you're open for any questions, so people should just approach you if they want to know more about specification.
Yeah, definitely.
Yeah, and thank you very much again. It was a very, very nice talk. Nice to have you here, and have a good day.
Yep. See you all next year, hopefully in real life.
Yeah, hopefully in real life. Yeah, it would be much more fun.
Goodbye.
Bye-bye. Hello, everybody. Welcome back. Now we have a quite different topic, given the specification-driven design. We have a kind of more Haskell topic, but let me introduce our speaker first. He's Albert Krewinkel. And I think it was very interesting when I read like the career path Albert took, like from molecular biologist turned mathematician turned software engineer. That is quite the path. And I learned from his webpage that from his introduction in text that he is especially interested in publishing workflows. So it makes a lot of sense that he is a core developer of Pandoc. And besides that, he is the current maintainer, I think, of HS Lua, which is a bridge between Haskell and Lua. And he will tell us about, this bridge, not a really new thing, but a new implementation on how to do that. We will see how that looks, but also how it works and how they manage to bring those quite different languages to work together smoothly. So again, you can't really welcome Albert appropriately, so I will do it for you. So I give you Albert Krewinkel.
Hello everybody, welcome to my talk. I'm Albert. I'm gonna tell you today about Haskell and Lua, which are two very beautiful programming languages in my opinion. And they can be used together to make even better programs. So let's start a bit about what this is all about and what this all means. And I think the best way to understand where I'm coming from is to look at who's talking. That's me. I'm Albert, as I said. I'm interested in scientific publishing mostly. And I'm also like a huge Haskell fan, let's be honest, and contribute to Pandoc for some 7-8 years now. But I'm also the current maintainer of the HS Lua package, which is a Haskell package combining Haskell and Lua. I didn't write that, I took that over some 5 years ago, I think, and have extended it considerably in that time. If we look at the languages that I'm talking about, Haskell and Lua, we see that those are very different, at least when we take a high-level view. We see that Haskell is statically typed, Lua is dynamically typed. Haskell is a compiled language, Lua is an interpreted language. Haskell has lazy evaluation, Lua has strict evaluation. So they really as different as they can be, I'd say. And of course, this means they're used in very different use cases. For example, Haskell is used for web gateways and window managers, while Lua is used for web gateways and window managers. Well, more seriously though, the difference, in my personal opinion, is that Haskell is excellent for projects that are really complex systems that you may want to maintain for a long time, want them to be easy to maintain. And Lua is just great if you want your program to be scriptable and extensible and want to mix different parts together. And you can probably see where I'm going with this, because if you want both of these features, then you may want both of these languages. And this is what this talk is all about. We look at an example first. Of course, we're going to use Pandoc. And Pandoc works by converting documents into its internal document AST data structure. Here you have a small example or small snippet of what the internal data format looks like. For inline text, you can have either plain text, or you can have emphasized text, or you can have small caps, and all this is mixed together. And so when Pandoc reads a document in, this is what it's represented as internally. If you look at the table, you'll see an example where on the left side we have the markdown input, and on the right side the Pandoc AST that results from it. And the first two rows give the same result in the Pandoc AST, even though they're different. So in Markdown you can either use an asterisk or an underscore around a word or a sentence and make it to mark it as emphasized text. But you can also combine those, in which case you have nested emphasis, which in a way doesn't really make sense, at least not if you nest it directly, but that's possible in Markdown. And you may go, okay, if it doesn't make sense, then maybe you can use it to represent small caps, for which there isn't any kind of syntax in Markdown. And of course, we could patch Pandoc and rewrite the parser and everything. But we could also say, okay, we have this AST, we want to convert it. Can we do that? And we can, and we're gonna use Lua for this. Because Pandoc has a feature called Lua filters, and it allows to write some Lua code, which is then applied to the Pandoc AST. So in this example, we match on, or we take all emphasis elements. And in this example, we check if the first element in this emphasis is also an emphasized text. And if it is, then we take the content of the nested env element and we turn it into small caps. Below you see how this works in practice. If you put like underscore star a word star underscore into Pandoc and convert it to LaTeX, you get these nested emphases. But if you also use the filter above, then suddenly the whole thing is turned into small caps, which is exactly what we want. And as you can imagine, this is immensely useful. So, how does all of this work? Well, first, we already saw the languages are different, but they also have a lot in common. For example, they both allow for functional programming. Lua has functions as first-class objects. They both garbage collected, which is neat, but also leads to problems if you imagine two garbage collected languages working together. But the most important point here is they both have an excellent C API. And this is what we're going to use to link them together. And I'm going to show you how. So let's first talk a little bit about Haskell's FFI. That's the foreign function interface. And it can be used to, to connect programs that are written in a different language. Of course, we need the relevant types that are present in that different language, and we need to get it into our runtime system, and that's what we look at now, because we can use function imports. So if we have something like a C function, I'm using a Lua example here, Lua push boolean, and that function takes a Lua state, which is a thread in like a Lua thread, and an integer representing a Boolean. As you may know, C uses integers for Booleans, and it returns nothing, the void, the unit, basically. And we can translate that more or less directly into Haskell. The syntax is quite simple. We just write foreign import, define which language, calling convention we're gonna use. We say where the function is defined, and then we give it a name. In this case, we also use Lua push Boolean again. And then we're gonna use the types, the correct types, to make sure that everything works. So we have this cint, which is a C integer, and we have ptr, which is a pointer. In this case, we're cheating a little. We're using a void pointer, which can contain any kind of object. But you get the idea that this is how you bind to a function. As you saw, like the types are not especially sophisticated in C. So I think that's kind of the charm of C, that it's really simple, and that yeah, it's really close to the machine. But of course, in Haskell, we want our types to be very expressive and to make clear what they mean and represent. Just looking at the types, we want to know what something does or something is. And we can still do this in the FFI, and because we just need our types to be instances of the storable type class. So if we want to say, okay, this integer is actually a Boolean, like a Lua Boolean, we can define a new type called Lua Bool and use that instead of a cint. And we can do the same thing for a stack index, which is a very important concept in Lua. So we can define a separate type for that. We can still use it as a number, which is something we do not want for Booleans, but for something like a stack index, which is a number in a way, we want to be able to just write one, and instead of having to manually wrap it every time. And that way, we get quite more informative types and type signatures for the imported functions. And this is what the Lua package does. We provide just a number of bindings to normal Lua functions. And it's quite possible to use that, just that package. But what happens is that you basically have to write C in Haskell. And like, my personal opinion is it's not especially pretty. It's possible, but it works. But what we really want is we want the familiar feeling of using monads and everything. And the code you saw before, that was wrong. Let me switch back. Where we just get some H field from somewhere, and this looks not nice in my opinion. We want it to look the way it does here, and this is what the H is Lua package is all about, because we wrap it in a way that makes it very comfortable to use from Haskell. For that, we use certain tricks, for example, the reader monad, because the reader monad is more or less just a wrapper around functions that all take the same argument as the first parameter. So in the case of Lua, all of these functions always get the state as the first argument. And because monads are so nice to use in Haskell, we simply write this nice wrapper, which allows us to do a very monadic programming style. And it's still very simple in my opinion. Okay, so we have seen how we can bind all the functions, but what's about the data? Like, we need, all the functions are useless if we can't get data from Haskell into Lua and back. And the way this works is via a stack. So Lua has a stack for each thread. And if we, for example, want to call a function, we put the function onto the stack and then the arguments in order. Then we use an API function to say, okay, now call this function with 3 arguments and return 1 result, and Lua will do that. And so this is how we interact with Lua. So every time we want to get some data onto the stack or from the stack, we are then actually able to use it with Haskell. This is quite simple for basic data types like numbers, booleans, or strings, because Lua comes with this nice API. But things get more interesting if we look at random or data types we use in our Haskell application. How do we get those on the stack and back from the stack? Well, one way to do it is to use Lua tables. Lua tables are the Lua data structure. There's nothing else, basically. Although that's not true, but I will come to that. If you program in Lua, you'll be using tables a lot. And the API makes it simple to use, so we just define, assuming we want to push a pandoc inline to the Lua stack, we tell it to create a new table, then push the text, for example, that we want to have in the element, and then set that as a field. And in the Lua example, you see how that looks like, or how the equivalent Lua code would look like. It becomes just a table. There's curly brackets define a table, and it has a field and the content of that field. So if we then access the field, we get the content back. That's nice and simple. And it's actually what we used initially in pandoc, because there's one more thing that makes tables really nice, which are meta tables. Those meta tables can be used to define the behavior of a table, of an object, actually of any object in Lua. For example, if the meta table has a function, a special field, __add, then this allows to override or define the way the object behaves when used with the with the plus operator. So normally, if we look at this line here, this one, sorry, we see that using plus with a table doesn't work. Like this yields an error. But if we set a meta table, then we can actually use the plus operator, because suddenly it's defined and it makes sense. Well, it doesn't exactly make sense in this example, but you get what I'm going for. And just like the add operator, there are other things you can control, like indexing, accessing a field in a table can be overwritten. So in our example here, whenever a key isn't present in a table, we just return 42 instead. And you can see that at work in this example. So the first field is defined, it's 1. As you see, Lua arrays are indexed starting at 1. Well, it's a matter of taste, but I think in the Haskell world you agree that this is not that bad. And if we access something that doesn't exist, in this case the field hello, then we get back 42. We can control even more things, like the behavior when the object is garbage collected, which in the case of tables maybe doesn't make that much sense, but as you'll see, it's incredibly useful. So yeah, tables are nice because they're straightforward, the data structure in Lua, they're simple, and they're strict. Like strict evaluation. Whenever we want to push something onto the Lua stack, we have to evaluate everything. Like the whole value we are pushing has to be evaluated. Of course, that for people coming from Haskell, that may feel wrong, because Haskell's usually lazy. And especially with these huge structures that we may have in Pandoc, where we have an AST, a tree containing a complete document, we may be interested in just a tiny part of that tree. But often enough, we have to push the whole tree onto the stack if we use tables. That doesn't seem right. So, entering user data. Those help to put in arbitrary data basically into Lua. They are just a container, and that container can contain any data. And that the behavior of that container can be controlled via meta table. So usually those are used with pointers, but well, pointers don't work all that well if we look at a garbage collected language, because well, the garbage collector may move things around and then the pointer suddenly points to some memory that's no longer valid, and things go bad really quickly. But Haskell has a solution for that. It's called stable pointers. Those are not really pointers in the C sense, because they're not required to actually point to memory, but they are guaranteed that if you dereference them again, you get back the value that the pointer pointed to. So this allows us to basically hide things from garbage collection and to make sure that we always keep track of an object. Of course, once we're done, we have to manually free it again, which may be a problem in some cases. Why? Well, here's how we use them with user data. We just put a stable pointer into the user data, and that stable pointer points to an arbitrary Haskell value, which means that we can have our lazy Haskell value and put it into the Lua or onto the Lua stack via this user data. Here's the example code, which is quite simple to understand. I think it's first we create a new stable pointer and we create a new user data object, which is this Lua new user data, and it must be of the size big enough to hold this stable pointer, and then we write that stable pointer into the memory location that's given to us by the new user data. So we in the end we have just what we wanted, the stable pointer inside a user data. But the problem is, when do we free that stable pointer again? Because we maybe that user data lives forever, and it's enough if we free the pointer once the program finishes, but maybe we create a lot of them and we're not entirely sure like when they go out of scope in Lua. And happily we have the __gc meta method, because that one allows us to run any code every time the garbage collector realizes an object is no longer used, and this also works for user data, so the user data is collected. For performance reasons, we're not writing that function in Haskell, but we write it in C. And I think that's one of the most amazing parts, that this actually works, because Haskell has, like in the C API or FFI of Haskell, there's also a number of C functions that are defined. So we can include this hs ffi.h, and then we can actually use C functions that do actions on Haskell data. In this case, the stable pointer. So this is the function that we are using to free the stable pointer in user data. We get the stable pointer out of the user data. We make sure that there is, that we didn't make a mistake and this was called on something that is not a user data, in which case we just ignore that. But if there is a user data and it points to a stable pointer, then we free that stable pointer. So we can use stable pointers in Lua, which is beautiful. Now, if I was you, I'd be wondering, okay, but you don't seriously expect me to know all this and write this whenever I want to combine Haskell and Lua, right? And of course not, because we wrote a lot of code to make it easy to use, because naturally we want people to contribute to Pandoc to be able to understand the Haskell Lua bridge, and it must be easy to use. And so this is what the bridge looks like in action. Here's some code from Pandoc. And we're gonna look at a row, like a table row, which can have attributes and then a list of cells in that table row. And to make it usable, we just define a new type, which we call row. And we say, okay, it has a property called cells. And we also add a description, which we can use when we generate documentation for this. And then we define how this cell property behaves. Namely, it's a list of cells. So push cell would be defined somewhere else. And this is more or less a lens. So we define how the list of cells can be retrieved from the row object. And here below, the same thing, but in reverse. When we get it from the stack, the row object from the stack, we define how we would set a cell, the cells in the row object. Below here, it's an action. Again, this is how it looks like in Lua. We can use it just like a normal table or normal object and access the cell property. So basically everything works as expected, with the additional benefit of everything being lazy and only pushed onto the stack if we actually need it, and if we don't need it, it's simply a stable pointer. We also want to be able to use functions, which we have in Haskell, and I wrote a little embedded DSL for that. Without going into too much detail, the basic idea is to expose it by defining the attributes, the parameters the function gets, define how those should be retrieved or should be pushed. Should be retrieved, and then how the result should be pushed back onto the Lua stack. And of course, we then want to make it available to Lua, and for that we also have a nice function, and we can just use that and push it to Lua. So after that, we have a function that's called row in this example, and we can use it just like a normal Haskell, just like a normal Lua function, but it's actually a Haskell function. Then, with all this, we also, if we use that in a bigger project, we still want to be able to write tests for the whole thing, and this is why HSLua also comes with a project that allows to write tests. It's very simple, so it's not super sophisticated, but for me, it's all I need. Like, we can write basic tests, we can group them, we have assertions that we can use. And the beautiful thing is that we can integrate it into Tasty. So Tasty is this very popular Haskell framework that we also happen to be using in Pandoc. And we can just take complete Lua files, test files, and run them and integrate them into the Tasty output. So whenever we run a test suite, we actually also run the Lua tests, because things should be nice and everything needs to be working together for us. So that's kind of handy. Also, since Haskell is so well known for its property tests, of course, we also support property tests. So whenever we want to test that something works for all integers, for example, we can do so. And you may still not be convinced and be asking, like, okay, nice and all, but is anybody in industry actually using that? Well, first of all, we have Pandoc, which I mentioned a couple of times, and people are using Lua filters quite a lot, I think. If you check GitHub for repositories that have the topic pandoc and use language Lua, you get currently 41 projects, which I think is pretty good. The one with most stars is around 400 stars, so it's also quite popular. But there are even big companies betting on that. For example, we have Quarto from RStudio. RStudio is more or less rewriting the popular R Markdown toolchain using these Lua filters, and I'm fairly certain they wouldn't be doing that if they didn't trust the robustness of the whole stack. So yeah, there's actual quite a bit of investment into this thing. Okay, that's it. Many thanks for listening. If you want to learn more about it, here's a short list of links you might want to look at. I'm going to upload the code for this talk to the HS Lua website in just a tiny bit. So if you want to watch that again, you can find it there. And if you want to learn more about languages, you have lua.org, haskell.org. You can take a deeper look at how pandoc uses Lua filters. And if you're interested about Quarto, then please go to quarto.org. And yeah, that is it. Thank you.
Thank you very much. A very, very interesting talk, I think. At least I'm totally sold on HS Lua. I dabble a bit with Lua myself, and I'm getting into Haskell, and I can't wait to play with it, to be honest. I think we just do the same thing I did with Joachim. We just start talking, and hopefully then the questions will come in. Let's give the audience a bit time to let it sink in. Okay, my first question for you, Albert, would be you gave us quite a few glimpses on the inner workings. So what would you say was the most challenging aspect? What was it that took quite some time to get a grip on, or something like that?
Right. Good question. So I think the most challenging was actually the way basically the reason why I started getting into HS Lua. It's error handling, and I didn't get to talk about it because it's basically a chapter of its own. But there's some interesting stuff going on with error handling in Haskell and in Lua, which basically means we have to intercept all errors happening and must prevent them from leaking into other frames, like stack frames, because otherwise everything crashes. And that was surprisingly difficult, but also fun. Like, I should probably talk, like I said, that would be a separate talk.
Yeah, okay, I get you. So then let's just look at what I said. Like I'm totally sold on this, and now I'm wondering what would be a good I don't know problem area or something that I could start to fiddle around with HS Lua. What would you say?
I'd say if you have something that needs configuring, because like one classic example of using Lua is to use it as a configuration language. Of course, in Haskell, we have stuff like DAL, which can be used as a good configuration language, but still Lua is pretty good for that. And I think it's very like low entry because it's fairly easy and the objective is really clear, but it also is enough to get into the whole thing. So that's probably a nice thing. Or obviously, like start hacking on Pandoc.
Yeah, obviously. Yeah, I consider that. So I'm looking like come on, guys, come up with questions. Otherwise, I have to think of. Yeah, I don't know. It's late in the afternoon.
It is.
It is. I mean, maybe it's just a sign that everybody thinks like, oh, let's get into a break early, but I'm not there yet.
I mean, I can do like a quick intro into what I talked about. What's difficult with the error handling?
Yeah. Let's do that.
Because what Lua does is it uses the set jump and long jump, which basically just jumps around the stack. And if you call Lua from Haskell, then back again, then you have a C frame on the stack, a Haskell frame on top, and then we just C again.
okay.
And then if there's an error, the stack is cleared back to the initial frame, like the C frame, and it just deletes the Haskell frame. And then the Haskell runtime is not exactly happy about that.
No, I can imagine. Okay, no, I have a picture of what you said, like have break loose, like oh my god, yeah. Just delete the set.
So yeah, what that creates some problems also with performance because calls like going from C to Haskell and back is, well, it's not slow. It depends a little bit. There's actually, I have this slide, so if people are interested in looking at the FFI overhead and compare languages, I think this is really nice. I intended to include this in my talk initially, but then I unfortunately ran out of time. But it's a really interesting thing to look into.
Okay. Yeah, I'm just looking at the clock, so I'm just really a bit knackered, to be honest. I have a long day.
We all are.
Yeah, we all are.
Coffee's wearing off.
I'm just leaving it at that. So okay, if anyone interested in HS Lua, please look at Pandoc, right? Try consider contributing and overhead and stack handling, error handling really is like kind of the points where you kind of probably developed some headache before you I suppose you have do you have some place where I can see how you solved those problems, because I think you solved them eventually.
We did, yeah. It's in the repository link from the hslua.org website.
Okay.
Perfect. And yes, I should probably write a bit more documentation about it, but it's also documented on the website.
Okay. So then again, thank you very much, and to everybody else, like have a good break. And I don't know exactly what's coming up next, but we still have 2 talks, I think. Anyway, I'm out. Please. Bye.
Bye.
Okay, welcome back to track number 2. We're in the last block already, so the last 2 talks in this track at least. There will be a closing afterwards in room number 1, I believe. But now there's still 2 talks left, and the first one is by Laura M. Castro. She's a professor and lead researcher at the Universidade da Coruña. I hope that was correct. And Brujo Benavides, who's an Erlang developer and major open source contributor to the Erlang ecosystem. And they both talk about detecting Oxbow code in Erlang code bases with the highest degree of certainty. A warm round of applause for Brujo and Laura.
Hello, this is Laura Castro. I'm a professor at the University of A Coruña.
I am Brujo Benavides. I work as a staff engineer in Nextdoor, and I am a member of the education working group at the Erlang Ecosystem Foundation.
As I am too. And we are here today to talk to you about detecting Oxbow code in Erlang code bases with the highest degree of certainty. And of course, the first thing would be to clarify what we mean by Oxbow code. And we're going to do that by telling you a little story that we hope you can relate to. So imagine you have in a large project a module with, in this case, one function. It's called run. You can see it is exported in the third line of the snippet that you see on the screen. And it doesn't really matter what the run function does. Just it's some code that can be invoked from outside this little module. Now, in your development day-to-day, one day you get a ticket saying that we want to slightly modify our project so that the run function can sometimes be actually invoked and some other times won't be invoked, just for some A/B testing and for whatever reason. So you roll up your sleeves and there you go. First thing you do, say it's create a configuration parameter. Well, you call it sample rate, and it has a value, and it will be in one of your project configuration files. Then you go back to your module, but since you're a very thoughtful developer, you're going to do some test-driven development. So first thing you do is codify the 2 main tests for the 2 situations, the one in which the sample rate will tell you that you don't want to run the function. That will be the ignore test, the first on the right-hand side of your screen, when you can see that we want to assert that we are not running, we're ignoring what the function does. And the second test, in which you will actually indeed invoke the function and you will get the evaluated result because the sample rate is 1. So those are your tests, and of course, you run them, things will fail. So you have to go back to your code and start actually implementing things. First thing will be to, within the run function, actually retrieve that sample rate parameter, and just in case something happens and you cannot recover that from the configuration environment, you also have that macro on the third line that will be your default value to fall back to. So now you have a sample rate, okay, you have to use it. For that, you change your evaluation, your regular evaluation that you had before, for a maybe evaluate private function in which you will use the sample rate. And so sometimes, and you have a random value for that, sometimes you will actually invoke the function that will be the last part in yellow in the right-hand side, the maybe evaluate will actually call evaluate, but then right above that, the function class before will determine that the random value is higher than the default sample rate, and then in those cases we will ignore and will not invoke the function. That will be the functionality that was expected, and if you run the tests, then those will pass now, and you're happy. You move on to your next functionality. And maybe you even move on to a different project. Some other developer comes to this project, or just enough time goes by that when after some time, the need for that sample rate and the need for that differentiated invoking or not invoking behavior is not needed anymore. Of course, a new ticket will appear in In the ideal world, you would like to go back in your GitHub history and just remove all the commits that were related to that change. But there are a number of reasons why this may not be possible. You might not even be aware, if you're new to the project, that there was an original ticket doing exactly the reverse, or many other reasons. So, well, if you're left with only the code, you will inspect what's in there. And if you don't have to differentiate when to actually run or not run the function, then of course you go first to the tests, and you will remove the tests that are no longer needed, because that functionality is the one that you want to remove. You will end up with just the original test, the evaluate test. We want to always evaluate the function. The other we can remove. Then going back to the code, the part of the code where the decision is made to ignore, that is irrelevant now, so we want to remove that. And, well, that will be it. Functionally wise, I mean, if you run the test now, the test will pass. But I hope you are with me in that there are lots of code there that are not actually needed. In fact, we have this maybe evaluate that was introduced that you can see now that 3 parameters and two of them are never used. If you're familiar with Erlang, you also will realize that we have 2 underscores before run and rate. That's the way we usually show that we are not interested in doing anything with those parameters within that function clause. So, well, those could be removed. And actually, the whole maybe evaluate is going to be really easy to simplify, because there's a random unit value that is not longer needed, and that will get us back to having just a sample rate and a parameter and using the parameter to evaluate. Now, remember, this maybe evaluate function is private. So we may realize that sample rate is a parameter that even doesn't have the underscore, or at least it doesn't have the underscore yet, is not longer used. So the changes that we might need to do in the maybe evaluate will be contained within this module, because, as I say, maybe evaluate is not on the export line, that's the 4th line on the snippet. So since we have all the power to modify it and not affecting any other modules, we could just do that and get rid of the sample rate that we are getting from the run function, the core body of the run function. And from that removal, we will come to the situation when we realize that we don't actually have to inspect the environment, and we can just get rid of that. So we're backtracking, slowly backtracking the changes that someone did at some point in the past. Right, so that's the situation where we stand now, with all the gray things ready to be removed, and that will be almost as the situation we had originally. Of course, there's some things that, even if you would help yourself with code coverage, for instance, to know what things were not actually needed or used, there are things that will be beyond the scope of any other regular tool to help you, such as will be the case of the macro definition that is not longer used, but no coverage tool will make you aware of that. And of course, there's also the configuration parameter that at some point someone introduced in a configuration file that will also remain silently there. But it's, again, something that no one is using and that was not there at the beginning. So ideally, we would like to be able to say, hey, this and this should also be removed. And then is when actually we will be at the same point as if this functionality had never appeared in the project. So I hope you agree with me that we would like to have less code, because less code is less code to maintain. So it means a project which is easier to maintain overall, especially since we're talking here a small example, but we are aiming to extrapolate this situation to really large projects. So what will be the underlying problem in your own words, Brujo?
So basically, what's happening here is that as a developer, I'm faced with the risks of removing stuff. I don't know if I can remove things for sure. For instance, is this macro actually never used? Over here, it's defined in this very small file, but modules can be very large, and macros can be defined in header files. So a macro defined in a header file is actually unused. I have to check the whole source code to figure out if that's the case or not. And with libraries, that's even harder because header files can be shared across the borders of libraries. So I have to check them all if I have, say, a project with multiple ones. So it's not easy. And since it's not easy, and say I am a newcomer, I just arrived to the project, I don't want to enter the risk of removing that thing and then breaking something that I didn't even know about. What about this parameter? It's called sample rate. Once it's no longer in this part of the code, is actually unused? Well, to figure it out, if that parameter is actually unused, I have to first check that it's no longer retrieved in any place in the code, like this with application getemp. But I also need to check that it's not retrieved in a different way, say, getting all the variables from the environment and going one by one doing something. So maybe some piece of the code does that, and if I remove the parameter from the configuration file, I break that part of the code, which is in a completely different module, far away from the code that I need to change. So these two parameters were unused in this function. This was a not exported function. So as soon as I realized that no other function in the module is calling this function with something there, that's fine. But if the function is exported, I, again, have to check the whole project, all the applications and the libraries to figure out that these two parameters are actually unused. Or, to be more precise, they are unused. But if I remove them, I have to adjust the calls to this function from everywhere. And for instance, in this case, we are doing some computation before calling this. If I remove that computation, will I break something? In that case, the general feeling over here is, should I remove this? I don't know. And since I don't know, and I'm very careful not to break anything, I keep them. And I keep them here and in many other pull requests, one after the other, and these kinds of code pile up over time. They can be quite extensive within large and older code bases. So we wanted to create something to give developers the certainty they need to actually remove this and leave us with the proper and expected code base, the smallest one. So we created Hank. Hank is an Oxbow code checker. It's a plugin for Rival 3 that will help you detect pieces of code that are certainly not used, and you can remove confidently. It's extensible. Currently, it detects about 10 different types of Oxbow code. We call them rules. You will see in a minute. It's accurate. So if it tells you that you can remove that thing, you will be sure that you can. More on that also later. You can also define your own rules if you have some particularities that apply only to your code. And it's configurable, so you don't need to run every single rule on every single one of your code files. You can check and decide which ones apply to your project and where. What can Hank detect now? Hank, as of version 1.2.2, comes with 8 rules. The first one is unused record fields. In Erlang, there are structures called records that are composed by multiple fields. When you create them, you usually fill all the fields and use the fields whenever you need. But over time, some fields may become unused. But there is no tool that requires you to remove them from the record definition. And since nobody requires you to do that, you might not be sure that you can, and so you keep them. That makes your structures larger unnecessarily. So Hank will tell you which fields can be actually removed from the record, thus reducing the footprint, the memory footprint of your application. And also, as every other rule, reducing the amount of code you have to maintain, which is the main goal of this. As we saw before, you can have macros that were used in the past, but are no longer necessary. And Hank will tell you about them. Like the one on the example, it's in a module, but Hank will also check header files, and it will tell you if you have a macro defined for your whole system that you're not using anywhere. It will also tell you if the whole header file is not used anywhere. If you are not including that file in any module, that file is not needed, and so you can remove it. It will also detect configuration options that can be in your application description file, like the one we saw before, or in your config files somewhere. If you have configuration options for your application and you're not consuming them anywhere, Hank will let you know that you can actually safely remove them from the configuration. It will also detect unused function arguments for internal functions like the ones we saw before or the one in the example here, but it will also detect unused function arguments for exported functions, verifying that they are not actually needed anywhere else. Hank also comes with some slightly opinionated rules. For instance, one to detect if you are defining a behavior. In Erlang, you can define modules that use other modules as callbacks, and they are called behaviors, and the required callbacks are defined in the way that you see on the screen with the callback attribute. If you require other module to have some functions implemented, it's reasonable that you use those functions from within the module where you are requiring them. And if you follow that rule, Hank will tell you when you have defined a callback that you are not using in the module. And then for these two rules, I couldn't figure out how to write in a proper example on screen, so trust me, but basically, Hank will tell you when some header files, entire header files, or some attributes in header files are only used in one module. In that case, you can move them, you can move everything from the header file or just the particular attributes to the module where they are consumed. And that way, you simplify the process of development. In this case, it's not actually a removal, it's more like a moving thing. But the thing here is that when a macro or a record are defined in one particular module instead of a header file, you don't need to check the rest of your system to verify if they are actually used. You only need to care about the module where they are defined and used. And Hank will tell you when you can do that. And finally, if you have other stuff that you know it's Oxbow code and it's only particular to your system, you can define your own rules. You just need to implement the Hank rule behavior with two functions. Analyze, that will receive the abstract syntax trees of the files in your system, and some context, and it has to return the list of the list of Oxbow code pieces that it can find, and ignore so that people can specify which files or which functions or which macros to ignore. They are fine. We don't need to warn about those things. With these, you can either contribute new rules to the open source repository. Hank is open source, so you can contribute there. And if not, you can define them particularly for your system and just use them. The question now is how accurate Hank is. Will Hank tell me to remove stuff that cannot be removed in reality?
So Brujo was telling you about the specific behavioral rules of Hank. But the golden rule behind the design of Hank was accuracy. And what do we mean by accuracy here? Well, we could say that a tool that a developer cannot trust, or that he or she has to or can second guess, will not be of much use. So we wanted to people using Hank be sure that Hank will never have a false positive. So tell you that you can actually remove something when removing that cannot be or can lead to something being broken, as Brujo was explaining before. We're going to give that security, that confidence to people using Hank. So Hank will never be wrong. There can be pieces of Oxford code, so meaning code that is not actually longer needed. You could remove it. That will slip through Hank. So that could still be possible, and we talk about that a little bit more than in future work. But the ones that Hank will point to will be safely to remove from your project. That is the main idea, and that is the golden rule that rules the decisions that were made in the implementation, and still rule the decisions in the implementation of Hank.
All right, and so this was created a year ago, and we wanted to try to see how effective Hank was at detecting Oxbow code in projects. But for projects to have a large number of Oxbow code pieces, they have to be large and they have to be maintained for a couple of years, for a long time, because this thing is something that piles up over time, slowly but steadily. So we checked some large projects. We checked first Erlang OTP, the oldest Erlang code base in the world, and by some means, one of the largest ones. It's maintained by a large number of developers. Some of them are no longer in the project. They keep changing over time. So there is this whole situation of people have to implement things and don't really know the code base. Okay, so we tried to run Hank on it, and Hank actually found quite a lot of things. A lot of unused macros, a lot of unused record fields. It found many function arguments that were no longer needed, and even one unused configuration option. Erlang OTP is the code that runs everywhere. That code runs in every single Erlang project in the world. So cleaning this one up, it's a major feat. And so we contributed this report to the Erlang OTP team, and some of the things they found were done on purpose, but some others were actually unused code, so the cleanup already started. Then we checked another one of the very large code bases that are written in Erlang and are open source in the world. We checked Kazoo by 2600 Hertz. It's a very large umbrella project that is a repository with multiple projects within it. And it has plenty of files and with lots of developers that had worked on it. We found less stuff than with Erlang OTP, but still, we found unused macros, we found unused record fields, we found a lot of unused function arguments, we found header files that were not included everywhere, and 3 unused configuration options. So for reference, that's on a 400,000 lines of code, we found these pieces. And finally, we checked with a project that we knew that was very carefully maintained, Mongoose IM by Erlang Solutions. This project, I personally was part of it in the past, and currently I know the developers that worked on it, and I know how what the standards for developing this project are, and they are very high. And so we were expecting not to find that many Oxbow code instances. Still, we found 90 unused macros and more than 200 unused function arguments. So if the question was, is Hank useful? The answer is definitely yes. So
how useful do you think is being now after 1 year?
After 1 year, we know for certain that it's used in some very large code bases. The ones in Nextroll, where I work, we check every single project, open source or otherwise, with Hank, and we clean up a lot of unused code. We have some very large Erlang web servers with the code that's been there for a decade, so it was very fruitful. We know that it's also used in Klarna, and some pieces of Hank are included in the Erlang language server, which is also developed by people working for Klarna. So again, another large and old code base that is checked constantly now with Hank, also in Miniklip, Nova, and more than 30 open source repositories. The thing here is, once you put Hank on your continuous integration pipeline, it will prevent you from introducing Oxbow code in every pull request. And that's a great thing that helps people stay clean in this regard, like forever, as long as they use the plugin. And you can see that every day there are 1,800 or more downloads of Hank, and that's because the CI pipelines for all these tools, for all these repositories, include this tool, which is great. It's not the most popular River 3 plugin yet, but who can tell? Maybe someday, right? It's very easy to integrate on CI, particularly because it's a River 3 plugin, so you just need to add it to your configuration file and that's it. And it's generally fast, so it's usually a good addition to your continuous integration. Of course, it's still not done. There are many things to do in this tool and related stuff. For instance, Hank only. Ooh, spoilers. Anyway, for instance, Hank only works on Erlang, of course, so far, but the concept of Oxbow code applies to every single language out there. You will find similar tools for Java and other languages, but there are not too many. It's a fairly empty area of research and implementation. So you can take from this project the inspiration to build your own Oxbow code detector for your favorite language, particularly for other languages with similar code like Elixir. It's a great candidate. You can copy the rules from Hank and implement them as Elixir rules as well. Of course, as Laura was saying before, Hank doesn't currently detect every single instance of Oxbow code. We are sure that there might be some other rules that we didn't thought of it yet. So if you come up with an idea of some pieces of code that are no longer used in your system, just write an issue on the GitHub repository for River 3 Hank, and we can take care of it. Or, as I said before, you can implement your own rule and contribute to the community or use it on your projects only. And finally, there are improvements that can be made to the existing code base. Particularly, working with the abstract syntax tree of Erlang is not a trivial thing by any means. And what we did was some workarounds around some pieces of strange abstract syntax tree representation, particularly for macros and whatnot. So those things can be heavily optimized either in Hank or hopefully in the Erlang syntax modules in Erlang OTP. So if you wanna work on that, that will be highly appreciated for Hank and for other River 3 plugins that work with the same abstract syntax trees. There are performance optimizations. We followed Joe Armstrong's rule, so we made the code beautiful, and we didn't reach the point where we really need to make it fast, so we didn't. The code is still beautiful, and it's fast enough, but if you find yourself on a large project and some rule is taking too much time to analyze your code, just let us know. We can work together on the optimizations required. And of course, every rule comes with some particularities, some edge cases, and we aim, as we said before, for full accuracy. So if you find some edge cases where Hank is warning you about something that you can remove and you cannot remove it actually, open an issue on the repository and we will make sure to include that edge case in the rule definition.
So what we would like you to take home after this talk is the story that we presented here. If you related to it at any point and you're within the Erlang community, then you know that Hank is there for you. It's a reversive plugin, so very easy to incorporate to your daily routine of development. And it's a static code analyzer that will inspect your code base and safely tell you this can be removed with no second thoughts. And if you're outside the Erlang community, then you have an example of not only how to do it, but also how useful it can be, as Brujo was showing in the projects that were analyzed as part of the development of Hank, and also how the community is welcoming the tool and actually incorporating it to the different projects, at least the open source ones that we know about. If you want to know a little bit more about the inside of how Hank was made and well, all the little things that influenced the decisions, then there's an academic paper published at the Erlang workshop by Brujo and myself last year in 2021. You can very easily find it online, but if you don't, just reach out to either of us and we'll be happy to let you have a copy for yourself. And that's it from us for today.
So you can find us online with those handles. I am El Brujo Halcón everywhere. Laura is Laura M. Castro everywhere. And if you're on your way out, you wanna kill some dead code for us, it will help us a lot. Thank you very much.
Thank you.
Okay, thank you for your talk, Laura and Brujo. Very nice. Now we're in the Q&A. So far, I think I didn't receive any questions in the chat. If you have any questions, just post them to Markus Schlegel. That's me on the stage in room number 2. And so I can relay any questions to the both of them. The first question that's that's always coming up, of course, is: do you want to talk about anything that didn't fit in your talk, but you wanted to tell your audience anyway? So anything, any fun anecdotes during development, or any insight that doesn't belong in a talk but belongs in a Q&A maybe.
Funny anecdotes, there are quite a lot in this case. As I said in the talk, the Erlang abstract syntax tree is very particular. It was never built to be used outside of the compiler. And so whenever we started building tools using it from the outside, many developers ended up building our own parsers because the original one was not prepared to work on the code itself. For instance, particularly for Hank, the tools that come with Erlang OTP to parse Erlang code and provide abstract syntax tree already do macro replacement. So if you want to detect unused macros, you're screwed. You don't have macros anymore. So we had to adjust that. And the macros in Erlang, Elixir is a language created when we have learned a couple of lessons about Erlang, and one of the lessons was that macros were terrible, so they did it again in a proper way. And so macros in Erlang are very difficult, and there is currently no parser, and there are 10 of them. There is no complete parser for Erlang that provides all the information about macros. the one that Hank uses works for what Hank needs. So detecting the macros that are not used, but the Hank doesn't actually understand them. So 2/3 of the bugs that we have reported today are I wrote the macro incorrectly, and so Hank tell me that it's not used, and I was, what can I do? You know, but other than that, once the first rule was implemented, the rest of the development was pretty much straightforward.
Yeah, I remember a couple of discussions. I think it was over Slack that led, I think probably that led Brujo to add this opinionated disclaimer to most of the rules, at least the basic ones that were covered during the talk, are quite objective. But then at some point, and if people try to redo this work in other languages, they will find probably the same situation. At some point, you start to enter areas where you are affecting how people like to structure their code, and then that's some gray area. So that's a precautionary tale probably, but yeah, you just talk to your community, because sometimes that's also helpful.
Yeah, as well as I am the maintainer of Hank. Yeah, in the same way as the maintainer of Hank, I'm also the maintainer of a repository called Erlang Guidelines. And that repository has like 80, it's like the basis for a linter, but for human eyes, because some rules are very difficult to be checked by a linter. And Hank is predicated on people following those guidelines. If you don't, the rules will probably tell you that you're doing things wrong, and you have to ignore them. If you want to ignore the rule, you have to ignore. If you want to ignore the guideline, you have to ignore the rule in Hank. Otherwise, there are many things that will be very hard to detect with certainty.
Yeah, it's probably a a property of these languages like Erlang, or I'm working a lot in Clojure, that are not that statically like constrained, right? And programmers have a wider range of opinions about how things should be written, I guess. And speaking of other languages, you already alluded to this. It could transfer. Your work could transfer to other languages as well. Would it transfer better to other like similar languages in regards to type systems like Clojure, which is also very dynamically typed, or does that not matter? Or is there any preference which languages would benefit the most from your approaches?
I don't know, from the perspective of somebody, of the developer of the tool, if you want to translate the code itself to other languages, you will have to be at least in a functional language.
Yeah.
Because part of the way this works is by assuming, for instance, a flat namespace where the same function, the way you call a function doesn't depend on where you're standing. It's the same function everywhere. So it doesn't do some smart analysis of I don't know, inheritance or class dependencies or templates or stuff like that. We don't have in Erlang. So if you want to translate the code exactly to other language, you have to be in a similar paradigm, I would say. The conceptual thing like Oxbow code does exist in other languages. It was actually defined for Java, I think, originally. So a similar tool can be applied probably to whatever language you want.
Mm.
Yeah, I was trying to think more like within the functional and declarative family, languages like Haskell, for instance, that are really strongly typed. There might be situations that we encounter in Erlang or Clojure that are not faced there because of the formalism of strictly defining your types that will prevent you perhaps to end up with things that you don't need. That might be the case, but still the situations where the compiler and the types do not capture use, which is, I think that will be the common
the common pattern here. That's, as Brujo was saying, that's a common problem. And it may very well the case be that within each language there's some particularity or some strength that you can apply to better implement this task. But then that's a task for the expert in the language that decides to clone Hank, so to speak.
Yeah, I think if somebody is going to implement a Hank in other language, they need not to jump straight to the code. The first task, and it was our first task, and it lasted for a couple of months. It's not like 1 or 2 days. It lasted for multiple months, was to actually write down the rules of what we wanted to detect. So we saw multiple times in pull requests where the removal of one thing left configuration parameters and some other developer who was more experienced. And just because of that, not because any other tool told him, say, hey, don't forget to remove that from that other file, totally unrelated. And so we were capturing those things for a couple of months until we were able to define what that means in a generic way, so we can implement the tool to detect those things. So if you're going to implement the same thing in other language, my advice is to do that. First, figure out what Oxbow code means in your language, and then do the heavy lifting to detect that with the tool.
So you're saying you should understand your problem first and then solve it.
Yep.
It's probably good advice for all sorts of programming and other things. Yes. So when you extend Hank with other rules, you have to implement these two functions or these two behavior methods, or what do you call it?
Yeah, functions.
Is there any other help, or is that just totally up to the programmer then to not produce any false positives? Like, is that just totally my fault then, or are there any guarantees beyond that?
No, it's entirely up to the developer.
Okay,
Yeah.
so
Yeah,
I could screw up badly there.
Yeah, we actually have a rule that we use for tests that it's called what was the name? Something like everything is bad or something like that. That basically reports every single line of your code.
Yeah.
Everything is Oxbow code, so you can just use it for tests to verify that it's actually parsing the thing correctly.
All right. I think we're running out of time now for the Q&A. The next talk is queuing up. And so thanks again to Laura and Brujo for their talk on detecting Oxbow code in Erlang projects. Thank you.
Thank you.
Thank you. Bye.
Okay, welcome back after this short break for the last talk in this track number 2. After the talk, there will be a closing event at 6, I think. And I believe you should go to track or room number 1 for this case. I'm not sure if this stream relays that same event. So in any case, please go to room number 1 afterwards. Not now, because now there's still a talk by Ragnar Moog coming up about local first distributed applications with Rescaler. Ragnar is a researcher at TU Darmstadt, and he's working on, well, Rescaler, I think, mainly. And he can tell you more about that.
Hi, I'm Ragnar. I'm a programming languages researcher in the software technology group at the Technical University of Darmstadt. And what I'm going to talk to you about today is a mixture out of my own research, related work, and what I think is good practice in general. Programming language research is really about tying together the intent of developers and what you can efficiently execute on a given platform. In particular, I'm looking at very declarative programming models or programming paradigms that are well fit for distributed, decentralized, and coordination-free settings. Today's talk is about local first distributed applications. We'll start with a concrete example, the To-Do MVC case study, a type of application I think you're all very familiar with. It reacts to user input by updating its internal state and displaying that back to the user. You can also modify the state, resulting in this time-changing behavior typical for this kind of application. And while this is a small example, I believe you can all see how realistic applications are composed out of these same principles. Today I don't want to show you a single instance of this application, but rather multiple instances, because I own multiple devices and I want to collaborate with my colleagues. First, I establish a connection between device A and B using this three-way handshake for a WebRTC connection. Once the connection is established, both of the devices are synchronized. You can establish multiple pairwise connections, forming arbitrary peer-to-peer connection between the devices, and changes are propagated along the established connections. Now, as an array distributed system, you have to consider what happens in the case of failure. For example, what happens if device B crashes and is restored, which I'll simulate here by reloading the frame. Now, first you don't see much, because the state of the device B is transparently restored. However, changes are no longer synchronized. You can still work offline, and once you reconnect to devices, the state is synchronized again. And most importantly, once all of the devices are able to communicate, the state of all devices is consistent, a property known as eventual consistency. The to-do list is one example of a personal productivity application, a type of application I believe you're all very familiar with from your own work. However, local first applications are ubiquitous in many areas. Consider the many domain-specific applications that handle specific business use cases, where different branch offices or people working from home also need to collaborate. And finally, consider non-graphical cases, which are very typical for cyber-physical systems, such as this smart streetlight, which has a couple of sensors, a processing unit, and an actuator, which may realize applications such as detecting people nearby, and then all of the streetlights in the vicinity turn on their lights. There are many more examples of cyber-physical systems, such as cars, factories, and home automation. What all of these applications have in common is their usage scenario, which has a strong focus on local computation and data. That is, data is generated from local inputs and in reaction to local events, and also processed and used locally. While at the same time, there's a need for ad hoc collaboration, so collaboration with others that happen to be available, or collaboration with other devices that happen to be nearby. As a second part of setting the stage, we will look at the evolution of the platform these applications are executed on. Starting with this mainframe model, where you have one centralized computer which handles all of the computation and data, and multiple users make use of this computer in a time-sharing fashion. And here, collaboration is really easy because one user just leaves the data for the next user to use. Now, from this model, we have two separate evolutions. The first one are personal computers, where each user has their own device, and these devices have become very powerful, so they can really handle all of the things the user wants to do with the device. The issue with this model is that once we want to collaborate, we have the problem that we somehow need to exchange information, exchange state, and there isn't really a good common way to do so. What happens in many cases is that the application running on the device makes use of the user for this collaboration. So the user exports the state, sends that state, say, as a Word document to another user, who imports the state back into the application, exchanges, and sends the Word document back. And this is a workflow I still use every other week. Now, this can be automated better in the second development we had, which is the traditional client-server model that has obvious similarities to the mainframe. Now, the client-server model has evolved a couple of times. First, because we got so many clients that a single server couldn't handle them anymore, which resulted in a single data center handling many, many clients. And then, because clients are geo-distributed, the data centers also became geo-distributed. This is what we nowadays call the cloud. And the cloud is really great if you want to have all of your data in the data centers, say for the Google search index or the Amazon storefront. However, in a local first setting, all of the data and the computation and complexity is at the local devices, the cloud really is just a liability. Consider, for example, when device A is your car's navigation system and device B is your smartphone where you've planned your route. Needing the cloud to synchronize between these two devices means that both need to be connected to the internet, while really they could just communicate directly. What we really want to do is to enable collaboration between two devices independently of the concrete network topology in between them. In particular, we want to be able to make use of direct connections as much as possible. As a side note, if you have a cool service in the cloud making use of computation and data there, then you can just add the cloud as another peer in this setup. To summarize, our platform consists of these very powerful but independent devices that can do everything that the user wants to do locally, but they also have to deal with varied network connections. In particular, they should not assume that any centralized coordination is available. Given that we now understand what the usage scenario and the platform of local first applications are, the remaining issue is that developing local first applications is still considered as hard. Developing an application is easy if the use case can be directly expressed in the chosen programming paradigm and these abstractions can be efficiently executed on the chosen platform. However, in the local first case, both the use and the platform are far away from the paradigm we use to express these applications. And what we really need is a paradigm that's much closer to both the use and the platform. To find such a paradigm, we're now going to look at the technical challenges that we need to address. The first challenge is interactivity, where the to-do list application is no longer in control of what's going to happen next, but rather is driven by these external interactions. Now, interactivity expressed in a sequential programming paradigm leads to this problem called callback hell, where some interaction triggers an observer, which changes some state, triggering a new observer, but then a new action comes in, and then everything becomes a mess. Because the sequential paradigm and the sequential control flow is really not able to express externally driven changes. And this leads to a category of bugs called glitches, where a glitch is an interaction that's unwanted between different actions. For example, here's a file open a dialog with the presentation selected, and you can take two actions, pressing the down arrow to select the notes file or pressing the enter key to open the presentation. However, after pressing enter, there's this 200 millisecond delay, and if you wait, the presentation opens. But if during this delay you press the down arrow, then the two actions interleave and the notes file is opened, which is something you never wanted to happen. And if you observe today's applications, you find glitches everywhere. In particular, the reason why you often have to restart applications or restart your computer is to fix these inconsistencies that have snuck into your program. And this is really bad in typical cyber-physical systems, where continuous operation is necessary and we really can't afford these consistencies that may lead to catastrophic failure. The second major challenge is partial failure, which is especially bad in a local first setting because you can no longer apply the traditional strategy of replacing failed devices with fresh devices, because in the local first setting, each device is unique and important. Collaboration is the conceptual challenge of distribution. So let's look at why collaboration actually is so hard. But first, let's consider the centralized case, where we collaborate using some coordinator, starting in some empty initial state, and then device A does an action leading to this new state, device 2 does an action B leading to this new state, and we get this nice sequential progress of states over time. In a decentralized setting, we still have our two devices that do their own actions. However, we no longer have this global state, but rather these two diverged timelines of states. We still want to end up in a consistent final state and optimally the same consistent state that sequential actions would have brought us to. So we somehow need to merge these states in the middle. And merging really is a conceptual thing and could be all of your collaborators sending you their parts of your report draft and you combining them into one final report. And this workflow of manual merges works pretty well in a professional setting, where there are experts that know what merging should be. In general, however, this is really error-prone, and any errors lead to inconsistencies which we really don't want. So we kind of need to make sure that this merging somehow happens automatically. So let's take a step back and consider what should a solution provide, starting with some existing solutions, such as the classical cloud client setup, where a lot of consistency is provided by infrastructure running in the cloud, such as distributed databases, eventually consistent data stores, and things like that. However, remember that, again, all of the computation and data, all of the complexity is at the client, and the consistency in the cloud really doesn't help much for developing this client. Now, there are approaches that kind of extend this consistency border into the client with things such as client-side databases. However, they remain with this client cloud abstraction, where there's some border inside of the client between the interface that's consistent, provided by the data store, and then all of the user-facing parts of the application that still need to ensure consistency manually for the user. And what we really want to is a model where consistency, or the border of consistency, is up to the interactions between the user and the device, and consistency is also ensured over these collaboration borders between devices. The meaning of consistency actually depends heavily on the use case and what your goals are. So let's rephrase this to make it more concrete into how to automate reliability. But reliability means that in all cases, no matter what failures or what challenges arise, we want the application to behave as specified by the developer, such that no inconsistencies are ever introduced. We do propose a solution, Rescala, our library-based extension to the Scala programming language. Specifically, Rescala provides a declarative programming model that uses reactives to handle the challenges of interactivity and conversion data types to handle the challenges of collaboration. Both of these are combined using transactions, and then the message dissemination layer handles decentralized communication. Reactives are at the core of the developer-facing part of Rescala's programming model. A reactive represents a time-changing value that is defined by some computation, usually by depending on other reactives. For example, signals and events are two types of reactives, where signals are always defined and events are only defined when they activate. Si and Ei here are input signals and events which are assumed to be generated from some external interactions. You can derive new events from existing events, for example, by mapping using some function, accessing some signal value in the process. You can also convert events to signals, thus accumulating state over time. And you can use arbitrary Scala expressions to basically access signals and events in whatever manner you desire. Because of the dependencies between reactives, they form a data flow graph, with nodes representing the reactives, inputs at the top, and data flow along the edges. If you remember the to-do list application, it has this one input to create to-dos, it has the button to remove all done to-dos, and for each to-do, it has this little X to remove that particular to-do. This is the code of the to-do list, specifically the part that handles the list of to-do items. You can see the remove all input, which is coming from the UI, the create to-do event, another input from which we derive this create task event, where a task graph is the in-memory representation of each entry in the to-do list. And these task graphs have these task data, which internally have these little remove single to-do buttons, which is then represented by this remove click event. So all three of these input events flow into this large signal down here, which is a signal of a replicated list. So it's a list that changes over time, and it changes every time one of these three events occurs according to a specification done by some Scala function. And then this overall task list is later used in the representation of the UI, such that all of the changes you make are immediately visible. Now, going from the representation of the interactivity and the data flow graph to the question of how we handle these replicated data structures, which are part of the graph. So here again, we just have the definition of the task list, which is a signal of a replicated list. And we can then actually do the replication of such a data structure by just asking the network runtime to replicate this signal given a registry which defines the connections to other devices and a name which defines how other devices find this specific replicated reactive. To ensure consistency, in addition to the above, we also need an instance of type lattice of replicated list of task graph. If you're familiar with type classes, this is Scala's way to represent them. If not, consider lattice as just a normal interface that we need to implement for this replicated list type. So lattice of A, which means that A is a lattice, has a single method, merge, that takes a left A and a right A and produces a new A. In addition, we must ensure this method is associative, commutative, and idempotent. This is the only thing a developer of such a data structure ever needs to ensure to guarantee distributed consistency. If our merge function fulfills these three properties, then the space of all states in our system has a structure that looks like this. Merging two states A and B results in a new state AB, which is the least upper bound of the two merged states. And the really nice property about these least upper bounds is that no matter the order we merge things in, and no matter how often we merge things, we always end up in the same state. Thus, the least upper bound, or more concretely, the properties of our merge function, precisely address this issue we had with collaboration, where we have these two diverged states which we somehow have to merge into a consistent state. If and only if the state space forms a lattice, then we can always do these merges automatically. Having covered the theoretical side, the question then is, how do we actually implement a replicated list, and how do we obtain a lattice? First, you have to understand that a replicated list is a composed data type. Concretely, this means that our replicated list type is just a triple out of a G list, which is a replicated list where you can only add but not remove. And a dot is a globally unique timestamp. We also have a map from dots to nodes, which we use to track removals, and we have a set of dots for causality information. To acquire a lattice for our replicated list, we make use of its composed structure and the fact that lattices also compose. We define a lattice for any triple A, B, and C, given that A is a lattice, B is a lattice, and C is a lattice. By merging the left and the right triples, just merges the components individually. Relying on composition to derive new lattice instances is the major advantage for developers, that associativity, commutativity, and idempotency are provided automatically. And this is the only thing we need to rely on to ensure consistency. So all composed lattices are always correct. Only manual merge implementations need to be proven. The only remaining piece to complete our replicated data type are the operations to insert and remove elements from this list. However, during the implementation of these operations, we do not need to concern ourselves with any of the challenges of distribution, replication, or consistency, because it's not possible for these operations to invalidate the properties provided by our lattices. We can thus focus on the functional correctness, making sure that insertion actually inserts and removal actually removes. In summary, our state, merge, and operations combine into what's known as convergent replicated data types, or CRDTs. And while CRDTs are widely used in geo-distributed database systems, ensuring causal consistency and high availability, we believe that a language integrated approach, where the state is just an algebraic data type, merging just defines a category of states, and the operations really are just functions, enables application developers to compose and combine these smaller pieces into data structures that really represent their core application logic, as opposed to typical CRDT implementations, which are provided as black boxes, where developers somehow have to fit the application into whatever interface the CRDT provides. Now we've seen how reactives handle the challenges of interactivity and convergent data types handle the challenges of collaboration. However, if you remember our goals, we wanted to achieve consistency from one user to the other over these collaborative edges. And what we currently have is a declarative programming model for these interactions, and we have a way to achieve consistency on this collaborative edges, but we really need to expand this consistency to the overall application. The way we do this is by ensuring that the data flow graph itself is a lattice. First, by defining its state. We've already seen the task list, which is a signal of such a replicated data type. The task data is the representation of the individual to-do items, which is a signal of a last writer wins, a different replicated data type. These two data types are the values of these nodes in the data flow graph. Now, in addition to the state, we have to think about the operations. The data flow graph itself handles arbitrary incoming interactions. So the question is, what is the concrete set of possible operations we can do? And this is where transactions come in. So transactions group reactions that happen at the same time. For example, if this input up here changes, then all of the derived directives also have to change conceptually at the same time. And we ensure this in our runtime environment using our transactional mechanism, and then each transaction becomes a single operation. It leads to the following local execution model, where we have some initial state and then a transaction A, which changes the screen part of the transaction, resulting in a new state A. Now note that this transaction changes both values of the nodes in the existing data flow graph, but it may also add new nodes to the data flow graph, as Rescaler supports fully dynamic graphs. Then we may have a transaction B and a transaction C, again, both doing their changes to the data flow graph. Now, as a technical note, what we consider a transaction in the model that transactions are operations is basically this green part here. So a transaction is a function that takes this initial state and essentially produces this green change part, not the full new state. And we'll see why in a second. After defining the state of the data flow graph as the association between the nodes and their values, and the operations on the data flow graph as the transactions, the question remains how to merge two states. And the answer is that we again use composability of lattices to derive a new lattice for the data flow graph, similar to the merge function of tuples, where we merged all components of the tuples individually. The merge function of a data flow graph merges the value of each reactive in the data flow graph individually with the corresponding value of the corresponding reactive in the other data flow graph, producing this new value. If a reactive was only changed in one of the two transactions we want to merge, like this last writer wins reactive here, which is not changed on the other side, then we just keep the value of that reactive as is, which is equivalent to merging it with an empty state. You may now be wondering, what about the reactives that are upstream from the two derived reactives? So the three inputs and this one derived reactive up here that seem to exist in both states, but not in the merged result. This is because we distinguish between replicated reactives, which do have correspondences in other states, and all of the other reactives, which don't actually have corresponding reactives in the other state, even though they look structurally similar. And this makes sense because, for example, in the to-do list, we do want to replicate all of the to-do items, but we do not want to replicate the input fields where the user types the current to-do they want to add next. So even though both devices may have such an input box, these are two separate things. They never exist on the other device, so we also never need to merge the state, and we don't even need to include the state in the merged result. An exception are reactives derived from replicated reactives, which should be consistent as they are derived from consistent values. Now, we cannot merge them directly because we don't have a merge function for their values. However, derived reactives are fully specified by the computation that computes their value from the inputs. So for the merged value, we simply also recompute the merged result from the merged inputs. Now we've seen how reactives and convergent data types are combined and handle the challenges, but what we've seen so far is very much the programming language, design, and implementation side. What I also want to talk to you about is replication from the system side. So let's look again at one of these collaborating device diagrams, where we again have our two devices starting in states B and state BC. And now if device 1 in state B does a transaction, remember, transaction results in this kind of delta state only with the changed directives, which we also call here A. And then we take this delta state and locally merge it to produce the full state AB. Now the advantage of this local merging is that no matter how the operations are implemented, this local merge ensures that all of our consistency guarantees remain. In addition, because we have this delta state, we can very efficiently send it to another device because the changes are assumed to be much smaller than the full state is. And the remote device, we just merge the state as usual to produce a new state. Now, we're in the situation where device 2 and device 1 are still not consistent, right? They're in different states because somehow device 1 never received this change C up here. And we can now, at any point in time really, just compute any delta, so any subset of this state, send this over, merge it, and achieve consistency. Now, while this computing state sounds somewhat hand-wavy, this actually is a huge opportunity for optimization depending on your concrete use case. For example, if you assume you have a stable TCP connection, then you can just always send these deltas and assume that they are applied on the remote side and you have to do nothing else. When your use case requires you to write your state on a USB stick, put that USB stick in a bottle, drop it in the ocean, and hope that your communication partner finds the bottle, then maybe you, instead of computing a small delta, always put the full state on the USB stick to send that over, because then the chances that you actually reach a consistent state are much higher. In addition, to allow you to optimize individual components for your specific use case, the modular architecture also allows you to introduce new functionality. For example, if you're worried that your bottle is found by someone you don't trust, and you want to encrypt the data on your USB stick, you can do so by introducing a new component that sits in between the convergent data types and the message dissemination layer and provides this encryption. Introducing this encrypted layer works by essentially implementing the interfaces of both a replicated data type and the message dissemination layer. So our encrypting data type has a state that essentially is a set of encrypted messages. And it has a merge function that, in addition to merging, also ensures that older states we no longer need are removed based on metadata without needing to know what exactly is inside of the state. This is a performance optimization. And then our operations are sending and receiving and recombining these states. We're sending encrypts and recombining decrypts the state within this data structure. Note that we did not have to take care of any of the networking logic because that's handled by existing message dissemination layers. And we also do not need to adapt any of the existing application logic. In summary, Rescaler provides library additions for a declarative programming model to the Scala language, from which we can derive this transactional data flow graph, which is both really good at defining interactive applications of all types, but also has this fundamental mathematical model of how to deal with collaboration such that no matter what kind of network failures you have, your application semantics always remain the same. The remaining question is it fast? Short answer, yes. Longer answer, it depends. So on a 144 Hz monitor, if you want to update 100 directives every frame, you have 7 milliseconds to do so. Only 11 microseconds are used for Rescaler's transaction logic And the remaining 99.7% of the time, your application can do whatever it wants. Performance of distribution, replication, and network communication is even more heavily dependent on the chosen use case. So it's really hard to give one single answer here. However, to at least give you an intuition, I show here a comparison between a rescaler implementation of the to-do list, a implementation using Twilio Sync, which is a commercial synchronization framework using a centralized server, and an implementation using Flask, which is a Python web framework. As you can see, for computation, Flask is much faster than the other two solutions as it doesn't achieve any kind of consistency. However, we were actually surprised that Rescaler is comparable to Twilio because Rescaler has to do much more local operations to ensure consistency. But really, the important point of most applications is that as soon as any kind of centralized coordination is involved, network latency really dominates all other tasks. Because in Twilio's case, whenever you want to add an item to the to-do list, you have to wait until the server answers, which actually introduces a latency that's very noticeable to the user. If you'd like to see more benchmark and more concrete numbers, you can find them in the Rescaler repository or in our published papers. In general, the two trends I've shown you are confirmed by all the experiments we've done so far. While this is not part of Rescaler proper, we've shown that you can take the static data flow graph subset of Rescaler and compile it to sequential code that has no overhead compared to handwritten C code, which allowed us to implement the programming model in a way such that it can run on an embedded device, specifically on a Wi-Fi chip. This means that the overhead that we currently have really is just an implementation detail that we use as a trade-off to get more dynamic features and better integration into the Scala ecosystem. This concludes the technical part of my talk. I want to speak a bit about the social aspects, because even though I'm not an expert in that area, I do believe that reliable local first applications are an important piece in the data ownership puzzle. Some people call data the new oil, but then again, if you're not an oil company, what are you going to do with all the oil? A lot of companies don't even really know what most of their data is about. They just collect it for the fear that they are missing out on future wins. And I mean, storing data just technically is expensive. You have to pay for the storage. And most of the use of data comes out of very personal information, and making private data or very user-specific data secure is even more expensive, because things like the GDPR are very particular about health data, for example. With data being a liability, it's mostly large providers that profit from the current state of the art, because they build these centralized walled gardens and profit off of the data in a multitude of ways. This, on the one hand, stifles competition, which, on the other hand, leads to this issue that users are forced to use a bundle of mediocre applications just because those work well together and have access to their data. A language-based approach really has the potential in the midterm to provide data availability on the user's devices, where many different applications can make use of the same data and share data in a way that's comfortable to the user. This does not only foster competition, but also has this potential for mutual enhancements, where if your application provides a data source, this can also be used by others. Now, this model can also be seen in the provider setting, where the provider does have APIs such that others can provide these enhancements. However, this is never mutual, because as soon as the enhancement becomes popular enough, it will just be assimilated into the centralized platform, again reinforcing the current state of the art. While the social problems remain open and are likely things we have to keep fighting for in the future, other challenges, such as partial failure, interactivity, and collaboration, really do have good solutions in declarative programming models that extend and complement existing concepts that programmers are very familiar with, while at the same time having mathematical foundations that allow to address the challenges even in the most adversarial circumstances. This concludes the talk, but if you want to learn more, the best place to start is the Rescaler website. In particular, if you would like to dive more practically into the programming paradigm, we have a 1 hour, 40-minute video lecture that demonstrates how to write a distributed local first application starting from an empty Scala project and really going through everything step by step in a live programming fashion. You can also visit our research group, and there's lots of interesting and good stuff there. Or if you want to talk to me directly, feel free to send me an email. If you're even more interested in this topic, we're organizing a workshop on programming local first software co-located with eGroup in June. The workshop is very much about the topics I've presented here and will be in the form of presentations and discussions. You can submit your own proposals for talks about systems, about use cases, about things you need are important for this topic. If accepted, you will get a 30-minute talk slot, including some discussion. You can also submit in-progress papers. This is mostly targeted at researchers, which will also involve a talk, but we will also provide feedback on the paper with things you may want to improve, with other things you may want to consider. With that said, I hope to see some of you at the workshop, and this is it from my side. Thank you very much for your attention.
And we're in the Q&A section. Hello, Ragnar.
Hi.
So if you have any questions, please post them. As you probably know, you should post them to me, and I will relay them and sort of spin them into conversation. Me, that is Markus Schlegel. I'm on the stage. You can just, I think you can just right-click probably on my character, or you have to scroll through the list of all the names and find my name there. So as long as there are no questions, because I think we have a stream delay as well.
Yeah.
The default question is, of course, is there anything that came to your mind after you recorded the talk that you thought, should have said this and talked about this as well?
Well, maybe not so much a thing that I think I should have talked about, but something I didn't want to have in the recording of the talk itself, right? So I guess the more provocative thing I want to say with this talk is really, you should invest more into your language infrastructure, but really, because really, if you do these interactive distributed applications, or just interactive applications, or just distributed applications, if you have the right programming language infrastructure, it's actually much easier to implement them than it is to implement current applications. Like, even with all of the challenges combined, I think, like if you try to implement a distributed program in Rescala, it's surprisingly simple. It's just mostly sequential things, and everything else is taken care of for you, or you ignore the application logic and hand optimize some of the implementation details. I like to do that. And it's also surprisingly easy because, for example, I've shown you the to-do list, right? I'm pretty sure that the network layer has lots of bugs because it's really horrible, but it doesn't matter because the programming constructs, the lattices, ensure consistency anyways, no matter how buggy the implementation is, which is just such a pleasant way to develop. And, you know, it's much better than defining your Docker files, writing YAML all the day. It's just a nicer way to do applications. So I would really recommend you looking into these things. And it doesn't have to be Rescala, and don't cite me on that. You should use Rescala, it's the best. But even if it's not Rescala, like, implementing a framework like Rescala yourself shouldn't be too hard. Like, Rescala is maybe a couple thousand lines of code. Okay, it's a couple thousand lines of Scala code, but still, it's something that's doable. The important point is looking at the systematization, right? Finding the right abstractions you're using, putting them into this composable language context and using them all of the time. And then you can build lots of things very quickly. speaking of which, do we have any questions by now?
I think not yet. But speaking of composition, maybe I missed that, but you talked about how you can derive the lattice properties by just combining smaller stuff that already implements the lattices, right?
Yes.
In some ways. Is there also a way to not use this default implementation and provide your own custom merge, for example?
So let me see if I can find the slide. Seems too late. So the thing is, the way composition works in our case is using a couple of Scala specific tricks. So it's really a thing which doesn't have too much to do with what we are doing, but just with the fact that Scala has some compiler magic to automatically compose things if you want to. And you can't actually see any of that on this slide because I left it out to make it simpler. But you see here, for example, this triple lattice, right? And this triple thing is really what defines what composition looks like. But if you want a different kind of composition for your triples, you can just implement a different triple lattice. You can have as many as you want, and then just at the point where you use it, make sure that the right instant is used. That being said, for a lot of structured data types, like any kind of tuple, all of your normal data structures, Scala, plain old objects, beans, whatever you name it, maps, things like that. For all of these, there is pretty much always one lattice that makes the most sense, which I don't want to get into all of the details, but basically you can pretty easily define a lattice for functions, which is kind of function composition, but you merge the result of the two composed functions. And from that, you kind of can derive the semantics of lots of these composed data structures. And it's just kind of a thing where it naturally makes sense in lots of cases. One exception would be a lattice on integers, for example, where it's not clear what the primary lattice on integers is, because there are two, one that takes the maximum and one that takes the minimum, and really is very application dependent on which you choose. So Rescaler doesn't provide a default, but then again, also selecting the max or the min function isn't too complicated for developers. And there's various ways to structure this in your code base, like using imports or giving explicit names, or all of the things that your language offers. And if it's not Scala, any other language also has these mechanisms for modularization for things, and all of the things I've shown you are meant to integrate well with whatever your language does. I think that's also really important, is because languages are really good at composition, really good at modularity. So enhance that. Don't work against it by using all of these external additional things.
Okay, so still sadly no questions, or maybe they don't reach me, but
well, it's late in the day.
Yeah, we're all, as Bianca said before, we're all knackered by now. It's a very nice word. Me especially, yeah. I can speak for myself. Yeah, speak of myself at least. And well, I think we're running out of time anyway. It's almost 6, and 6 means there's the closing event, as I said, in room number 1. So we should all move our little avatars over to the other room, and there's probably Mike waiting for us already over there.
Amazing.
Thank you again, Ragnar.
Yeah, thank you as well. And if there are questions, I'm still around for a while and gather, I think. And you can also reach me by email.
Okay.